Europe is building some of the most ambitious megaprojects on Earth right now. From the deepest tunnels to high-speed rail corridors, these colossal construction sites are reshaping how countries power themselves and connect across borders. Today, we explore the massive projects rising across Europe in 2026 and reveal the scale driving this extraordinary transformation. In 2026, one of Europe's most consequential transport megaprojects remains the Fehmarn Belt Fixed Link, the undersea connection being built between Rødbyhavn in Denmark and Puttgarden in Germany. Rather than a bridge, this project is a 17.6-kilometer immersed tunnel designed to carry both a double-track electrified railway and a 4-lane motorway beneath the Fehmarn Belt Strait. Its purpose is to remove one of the main bottlenecks between Scandinavia and continental Europe and to create a faster, more direct corridor for passengers and freight moving through the north-south axis of the continent. The construction method is what makes the project technically distinctive. The tunnel is being built from large prefabricated concrete elements produced on land at a purpose-built factory site near Rødbyhavn. These massive sections are cast in controlled conditions, fitted out internally, floated into position at sea, and then submerged into a dredged trench on the seabed. Once aligned and connected, they are covered and protected, creating a continuous immersed tunnel structure. This approach avoids the need for a long bored tunnel while also reducing exposure to the weather conditions that would affect a major bridge in the Baltic. In 2026, the project is still defined by heavy marine and civil engineering activity on both sides of the strait. Work in that period includes continued fabrication of standard tunnel elements and special service elements, dredging and preparation of the tunnel trench, installation of completed elements in sequence, expansion of the portal structures, and large-scale land works connecting the immersed tunnel to the Danish and German transport networks. At the same time, rail and road approach infrastructure, technical building, power systems, drainage, and safety installations continue progressing in parallel because the tunnel itself cannot operate without fully integrated links to the surrounding network. The railway component is especially important in the broader European context. The fixed link is intended to reduce travel times significantly between Denmark and Germany and to strengthen freight capacity on a route that currently depends on ferry services. For passenger rail, the link is expected to support faster journeys between Copenhagen and Hamburg. For freight, it is meant to provide a more reliable and higher capacity crossing that fits into the wider Scandinavian Mediterranean transport corridor. The timeline attached to the project has long been central to its importance. After years of planning, approval processes, environmental review, and preparatory works, the main construction phase moved into large-scale execution in the first half of the 2020s. The widely stated target has been opening around the end of the decade, with completion generally associated with 2029, although final commissioning depends on tunnel installation, systems testing, and the readiness of the connected rail upgrades, particularly on the German side. Unlike conventional rail expansion projects, Stuttgart 21 is a complete reconfiguration of a major urban and regional rail node, while the city around it continues operating. In the context of Europe's mega projects under construction in 2026, it remains one of the continent's most important and most complex railway transformations, centered on replacing Stuttgart's historic above-ground terminus with a new underground through station and reorganizing the rail approaches across the wider region. The core concept is operational rather than architectural. The existing terminal layout forces many trains to end and reverse direction in Stuttgart, which limits capacity and slows long-distance and regional traffic. Stuttgart 21 converts the city into a through-running hub. The centerpiece is the new underground station, designed with 8 platform tracks set beneath the city, linked to a large network of new approach tunnels. This change is intended to improve improve network efficiency, reduce route conflicts, and support faster services on north-south and east-west corridors. By 2026, the project is still in an advanced construction and systems integration phase rather than an early excavation phase. The most visible work in that year includes continued fit-out of the underground station structure, completion of track systems, installation of overhead electrification and signaling equipment, tunnel finishing works, fire and life safety systems, ventilation, drainage, and extensive testing of railway operations infrastructure. Civil works are not the only focus anymore. A large share of the effort in 2026 is on converting completed structures into an operational railway environment that includes technical rooms, control systems, escape routes, platform equipment, and connections between the station box and the surrounding tunnel network. Another major part of the scheme is the set of new lines and tunnels connecting Stuttgart to the wider region. These include long rail tunnels through difficult geology and links toward the airport, the Messe area, and the Wendlingen-Ulm high-speed route. In 2026, works are still associated with completing these interfaces, finalizing rail equipment, and preparing the network for commissioning. The project is not just one station. It is a coordinated package of underground urban rail infrastructure, regional access routes, and integration with one of Germany's major high-speed corridors. Timeline remains central to how Stuttgart 21 is understood. The project has been discussed, redesigned, and contested for many years, with construction stretching far beyond the original expectations. By 2026, it is generally in its final major delivery period, but full completion depends not only on building works, but also on testing, approvals, and readiness across interconnected sections. The main commissioning target has been placed in the second half of the 2020s, with opening commonly associated with 2026 for key elements, although some related components and follow-on works may extend beyond that point depending on operational readiness. At the center of Europe's north-south transport system, the Brenner Base Tunnel remains one of the most important megaprojects still under construction in 2026. The project is being built beneath the Alps between Austria and Italy to create a new, low-gradient railway connection under the Brenner Pass, one of the busiest freight and passenger corridors crossing the mountain barrier between northern and southern Europe. Its strategic function is to shift more long-distance freight from road to rail, increase line capacity, and improve journey times on the Scandinavian Mediterranean transport corridor. The main tunnel system is designed as a base tunnel rather than a summit route, meaning trains pass through the mountains at a much lower elevation than on the historic Brenner line. This reduces gradients and allows heavier and longer freight trains to move more efficiently. The core structure consists of two main railway tubes running in parallel, connected by cross passages for safety and maintenance, together with an exploratory tunnel that has also served as a geological investigation and drainage structure during construction. When combined with the existing Innsbruck rail bypass, the continuous underground rail link reaches a total length that places it among the longest railway tunnel systems in the world. In 2026, construction activity is still focused on full-scale underground excavation, lining, structural completion, and railway systems, preparation across multiple lots on both the Austrian and Italian sides. Tunnel boring machines and conventional drill and blast methods have both been used depending on geological conditions. Work in 2026 includes further breakthrough progress in unfinished sections, waterproofing, final concrete lining, installation of invert slabs, construction of emergency and technical caverns, and continued development of cross passages between the main tubes. At the same time, interior works advance in completed stretches, including drainage infrastructure, cable routes, ventilation-related systems, and preparation for later installation of track, power, signaling, and communications equipment. Instead of expanding an existing airport, Poland's CPK program is structured as an entirely new national transport hub built from the ground up. In the context of Europe's mega projects under construction in 2026, Warsaw CPK stands out because it is not only an airport project, but a combined aviation, railway, and motorway infrastructure scheme intended to reorganize how long-distance travel functions across Poland. The planned hub located between Warsaw and Łódź, is designed to replace capacity constraints at Warsaw Chopin Airport while also acting as the center of a new high-speed rail network. The airport element is the most visible part of the program, but the project is broader in scope. The concept links a new central airport with long-distance rail lines radiating across the country, allowing major Polish cities to connect more directly to the hub and to each other. This changes the project from a conventional airport expansion into a national transport restructuring effort. The purpose is not only to handle more passengers and cargo, but also to shorten travel times, improve domestic rail integration, and strengthen Poland's role in regional logistics and international air connections. In 2026, the project remains in the main pre-operational construction and delivery phase. Work associated with that year includes continued site preparation, large-scale earthworks, utility relocation, land consolidation, road access development, and the early to intermediate stages of core airport infrastructure construction. Depending on the package, this includes groundwork for the terminal zone, airside platform areas, internal transport links, drainage systems, technical networks, and supporting service facilities. At the same time, rail-related works continue on planning, corridor preparation, design finalization, and selected enabling or early construction activities connected to the wider railway program that is meant to feed the hub. A defining feature of CPK is that the airport timeline and the rail timeline are closely linked but not identical. The airport is intended to open as the anchor facility, while sections of the rail program are delivered in phases. This means that in 2026, the construction picture includes both direct airport works and the longer process of creating the associated rail corridors. The railway component is strategically important because it is supposed to make the airport function as a national interchange rather than only a regional terminal. Without those links, the project's full transport logic is reduced. Rather than a single continuous railway built exactly as first proposed, HS2 in 2026 is a partially redefined high-speed rail megaproject still under construction in the United Kingdom, centered on the line between London and the West Midlands, and on the large station, tunnel, viaduct, earthworks, and systems packages required to make that first phase operational. Within a survey of Europe's megaprojects under construction in 2026, HS2 remains significant because of both its scale and the extent to which it is reshaping transport infrastructure, land use, and rail capacity in Britain even after major scope changes. The project's main purpose is capacity as much as speed. Britain's classic main lines, especially the West Coast Main Line, carry a mix of intercity, commuter, and freight traffic that limits flexibility. HS2 is intended to move part of the long-distance passenger demand onto a separate high-speed railway, freeing space on existing routes for additional commuter and freight services. In engineering terms, that requires a new purpose-built corridor with straighter alignments, major grade separation, dedicated stations or station alterations, and extensive civil works through densely populated and environmentally sensitive areas. By 2026, the active construction focus is on Phase 1 infrastructure between the London area and the West Midlands. This includes continued work on major viaducts, embankments, cuttings, bridges, tunnel drives, tunnel fit-out, retaining structures, drainage, utility diversions, and route-wide civil engineering needed to form the railway corridor. On the station side, construction activity continues at key locations such as Old Oak Common in West London and Birmingham Curzon Street, together with interchange-related works in the West Midlands. In underground sections, the project still involves tunnel boring, segment lining, portal construction, ventilation and emergency access structures, and later stage internal preparation for railway systems. In surface sections, 2026 work includes track bed formation, structural completion of bridges and viaducts, and progressive transition from heavy civils toward railway installation on completed stretches. A defining feature of HS2 in 2026 is that it is no longer understood as the full original network concept. The London to Birmingham section remains the core delivery program, while northern extensions that were once central to the overall plan have been cancelled or fundamentally altered. That makes the timeline more specific. Construction in 2026 is directed toward completing the first operational route rather than toward building the entire originally proposed Y-shaped national network. This distinction is essential in any accurate description of the project during that year. The program timeline has shifted repeatedly. The project moved from early preparation and land acquisition into full-scale civil works in the 2020s. But cost growth, political review, and scope reductions changed the schedule. By 2026, the line is still not near immediate opening. It remains in a prolonged delivery phase involving both unfinished structures and complex systems integration still to come. The expected completion and opening of the London West Midlands route is generally placed in the early to mid-2030s rather than the original earlier targets. Final timing depends on the pace of civil completion, installation of track, power, signalling, testing, and commissioning across the route and stations. Across Western Norway, one of the major road megaprojects still under construction in 2026 is the new Sotra connection, commonly associated with the replacement of the existing Sotra Bridge link between Bergen and the island municipalities to the west. The project is not limited to a single bridge structure. It is a full transport corridor redevelopment designed to replace an overloaded connection that has long been a bottleneck for commuter traffic, freight movement, and regional mobility in the Bergen area. The existing bridge and approach system have carried far more traffic than originally intended, creating recurring congestion and limiting reliability on a strategically important route. The new project is intended to provide a higher capacity fixed connection between the mainland and Sotra, improve traffic flow, increase resilience in the road network, and create better separation between different types of users. In practical terms, this means a new major bridge crossing, combined with extensive highway, tunnel, interchange, and local roadworks on both sides of the fjord approach. In the context of Europe's megaprojects under construction in 2026, the Sotra project stands out because of the scale of marine and urban edge civil engineering involved. Work in 2026 is not confined to one visible landmark span. Construction during that year includes continued bridge substructure and superstructure activities, foundations, pylons, or tower-related works, deck assembly or segment installation depending on the stage, and major approach road earthworks. At the same time, tunnel excavation and finishing, rock blasting, retaining structures, interchange construction, utility relocation, drainage systems, and local network reconfiguration continue across the corridor. The project is therefore a combined bridge and road program rather than a single isolated crossing. A central objective is to increase capacity on National Road 555, which serves as the primary connection between Bergen and the rapidly growing western communities. The corridor supports commuting, logistics, and access to industrial and offshore-related economic activity. Because of that role, the project has regional economic importance beyond simple congestion relief. It is meant to reduce travel time variability, improve operational reliability, and support long-term development on both sides of the connection. The redesign also aims to produce a more modern road standard than the older crossing can provide. By 2026, the construction profile is shaped by sequential delivery. Heavy civil engineering remains the defining feature of the year. Marine works, structural concrete operations, steel-related bridge works, road formation, tunnel packages, and junction integration are all part of the active build-out. Some sections may appear visually advanced, but a road megaproject of this type still requires long follow-on phases for pavement systems, barriers, electrical installations, lighting, control equipment, safety systems, surface treatment, and final traffic commissioning. For that reason, visible, structural progress in 2026 does not necessarily mean immediate opening. By 2026, the Grand Paris Express remains the largest urban transport megaproject under construction in Europe, and its importance lies in scale, network logic, and the number of separate construction fronts advancing at the same time. Rather than a single metro extension, it is a new orbital and cross-suburban rapid transit system being built around Paris to restructure mobility across the wider metropolitan region. The program includes new automatic metro lines, major line extensions, dozens of new stations, large interchange hubs, new maintenance sites, and extensive tunnel infrastructure intended to connect outer suburbs directly without forcing passengers through central Paris. The project is designed to address a structural weakness in the existing Paris transport network. Historically, many journeys between suburban areas required travel inward toward the center and then back outward again, creating inefficiency, crowding, and long journey times. The Grand Paris Express changes that pattern by building new circumferential and tangential routes. Its main components include Line 15, forming a large orbital route around the capital, together with Line 16, 17, and 18, which extend automated metro service into areas that previously lacked rapid, high-capacity links of this type. The program also includes major extensions to existing Line 14, which plays a strategic role in redistributing passenger flows. In 2026, construction activity is still active across multiple sections, although the exact stage varies by line and segment. Some parts are in advanced systems and station fit-out phases, while others remain defined by civil engineering. The year includes continued tunnel excavation in unfinished sectors, structural completion of station boxes, installation of track slabs, platform systems, power supply equipment, ventilation, fire safety systems, signaling, communications, drainage, and architectural fit-out. At the same time, works continue on shafts, emergency access points, technical buildings, depots, and surface-level integration around station sites. The project, therefore, combines underground heavy civils with railway systems, engineering, and urban redevelopment in parallel. A major distinguishing feature of the Grand Paris Express is the complexity of building inside an already dense metropolitan environment. In 2026, construction is not only about boring tunnels, it also involves managing interfaces with existing metro, RER, suburban rail, roads, utilities, and dense urban districts. New stations are often being built as interchange structures beneath or beside active transport infrastructure, which increases engineering difficulty and extends delivery timelines. Ground conditions, utility diversions, and urban constraints all influence the pace of work. Because of this, the program is best understood as a sequence of interrelated megaprojects under one name rather than as one uniform construction site. Timeline is central to any accurate description of the project in 2026. The Grand Paris Express is being delivered in phases rather than opening all at once. Some sections have already moved closer to operation earlier than others, especially where they are tied to strategic deadlines or have more advanced civil completion. Other sections remain scheduled for later delivery in the second half of the 2020s and into the early 2030s. That means completion depends on which line is being discussed. In broad terms, 2026 is a year of mixed progress, commissioning and finalization on some stretches, full construction on others, and continued network integration across the program as a whole. Spanning Estonia, Latvia, and Lithuania, Rail Baltica in 2026 is one of Europe's most important cross-border transport megaprojects still under construction, because it is designed to build an entirely new high-speed standard gauge railway through a region whose historic rail system largely developed to a different gauge and for different geopolitical and economic patterns. The project is not a conventional upgrade of an existing main line. It is a new north-south rail corridor intended to connect the Baltic states more directly with Poland and the wider European rail network for both passenger and freight transport. The strategic purpose of Rail Baltica is broader than travel time reduction alone. It is meant to integrate the Baltic states into the European standard gauge system, increase freight capacity, improve military and logistical mobility, and strengthen transport resilience along the eastern flank of the European Union. The corridor is planned to link Tallinn, Pärnu, Riga, Panevėžys, Kaunas, and the Polish border, with associated connections to airports, intermodal terminals, freight facilities, and urban stations. Because of that scope, Rail Baltica is best understood as a corridor program made up of many separate civil, structural, and systems contracts rather than one single construction site. In 2026, construction is underway on multiple fronts, but progress is uneven by country and by section. The year is defined by a combination of large-scale earthworks, embankment formation, bridge and viaduct construction, station and terminal development, access road works, utility relocations, drainage systems, and the continuing build-out of substructures for future track installation. In some sections, 2026 involves preparation of the railway formation and the structural completion of crossings over roads, rivers, and existing rail lines. In other sections, work is focused on station zones, airport interchanges, depot-related facilities, and environmental mitigation. The project's complexity comes from the fact that each national segment moves through procurement, land acquisition, and physical construction at a different pace. One of the central engineering features of Rail Baltica is that it requires a new railway geometry suitable for modern, high-speed passenger service and efficient freight operations. That means straighter alignments, grade-separated crossings, new bridges, new signaling systems, and a corridor designed to standards different from much of the existing regional rail network. In 2026, the visible construction is therefore not only about track, it also includes fencing, noise barriers where needed, road overpasses, underpasses, culverts, drainage channels, subgrade improvement, and the preparation of technical systems that will later support electrification, communications, and train control. Set inland from Crete's north coast, the new Heraklion Airport at Kastelli is one of Southern Europe's major aviation infrastructure projects still under construction in 2026. In the context of Europe's megaprojects under construction that year, it is important because it is not simply a terminal replacement, but a full relocation of the main airport function serving Crete's largest urban area and one of the Mediterranean's busiest tourism regions. The project is intended to replace the existing Nikos Kazantzakis Airport at Heraklion, whose coastal location, operational constraints, and surrounding urban development have long limited expansion possibilities. The basic structure of the project includes a new runway system, terminal complex, apron and aircraft stand areas, air traffic and support facilities, fuel and utility infrastructure, access roads, and associated flood protection and environmental works. Its purpose is to provide a more modern airport with greater long-term handling capacity and improved operational efficiency for both domestic and international traffic. Because Crete has strong seasonal demand, the airport is strategically significant not only for local mobility, but also for the island's tourism economy, freight flows, and resilience of transport access during peak summer periods. In 2026, the project is still in the active construction phase, with works extending across airside, landside, and access infrastructure. Construction during that year includes continued earthworks, pavement works for runway and taxiway zones, terminal building development, structural and architectural works, utility network installation, drainage systems, service roads, and technical buildings. At the same time, significant effort is directed toward connecting infrastructure, especially the road links needed to integrate the new airport with the wider Cretan transport network. This is an essential point in any 2026 overview because an airport of this scale is not operationally meaningful without reliable surface access for passengers, workers, logistics, and emergency services. The project is technically defined by the need to build an entirely new aviation platform on a different site, rather than expand operations incrementally at the current airport. That means construction in 2026 involves not only visible terminal progress, but also the less visible systems that determine whether the facility can eventually function as a certified international airport. These include airfield lighting, navigation-related infrastructure, security systems, baggage systems, power supply, water networks, wastewater handling, fire safety installations, and operational support facilities. A large portion of the work in this phase is therefore about transforming a civil engineering site into an integrated aviation environment. Timeline is one of the most important aspects of the Castelli project. The airport has been under development through a long sequence of planning, contractual, financial, and construction stages. And by 2026, it is approaching the later part of its build-out, but is not yet complete. The project has generally been associated with opening in the later 2020s, with 2027 often treated as the key target period for completion or entry into operation. Although final, commissioning depends on the pace of building works, technical system installation, certification, and readiness of the access road components. As with many airport mega projects, there is a distinction between substantial construction completion and full operational opening.
But how about one of the most impressive underground rail projects in Europe? The Jubilee Line extension initiated in the mid-1990s and opened in phases between 1999 and 2000. This extension added 16 kilometers to the Jubilee Line, stretching from Green Park to Stratford and including 11 new stations. This project tackled the acute need for improved transit solutions in underserved areas of East London and supported the regeneration of numerous boroughs along its route. Each station is uniquely designed, with Canary Wharf Station being one of the largest and most impressive, enclosed in a vast glass dome and supporting a daily footfall in the hundreds of thousands. The extension was not just about adding track. It involved sophisticated engineering challenges, particularly in constructing deep-level tunnels beneath some of the most densely developed parts of the city. A workforce of over 3,000 people was engaged, with a peak of 2,000 workers underground during the height of construction. The logistics of moving such numbers in and out of confined spaces safely and efficiently was a testament to the meticulous planning and execution of the project managers. One of the most notable features of the Jubilee Line extension is its integration of art and architecture within the public transport system. Each new station features works by different artists, making the line a cultural tour as much as a transit route. On the technical front, the extension required laying down enough concrete to fill 30 Olympic-sized swimming pools and enough steel to build 2 Eiffel Towers. The challenges were manifold, including financial overruns and delays that pushed the final cost to $4.3 billion, a figure that reveals the complex nature of urban underground construction. It's time to talk about the Hermitage Plaza in France, a transformative skyscraper project in Paris's La Défense district. Comprising 2 towers reaching 320 and 240 meters respectively, the project aims to integrate residential, office, and commercial spaces. Designed by renowned architect Norman Foster, this development has been in construction since 2019, with an expected completion date in 2025. Constructing such ambitious towers in the heart of Paris requires overcoming numerous engineering challenges. To start, the foundation work involved extensive excavation and the use of slurry walls to ensure stability in the densely populated urban area. The foundations reach deep into the ground to anchor the skyscrapers securely, a necessity given the height and weight of the towers. One notable construction method used for the Hermitage Plaza is the top-down construction technique. This involves building the above-ground structure while simultaneously excavating the basement levels. This approach allows for more efficient use of time and resources, ensuring that progress is made on all levels concurrently. The excavation was carried out using large diaphragm wall machines and hydrophrase technology, which help in digging deep and precise trenches filled with reinforced concrete. The core of each tower was constructed using a slip-form method, a continuous pouring of concrete that allows the core walls to rise steadily. This method not only speeds up the construction process, but also ensures the structural integrity of the towers. The slip-forming process involved around-the-clock operations, with teams working in shifts to maintain a continuous pour of concrete. The tower's steel framework was another critical aspect, requiring precision engineering and coordination. Large steel beams, prefabricated off-site, were transported to the site and lifted into place using high-capacity cranes. These beams form the skeleton of the towers, supporting the glass facade and internal floors. A significant challenge was the installation of the glass curtain wall, designed for energy efficiency and aesthetic appeal. Each glass panel was custom-made to fit the unique curvature and angles of the towers. Installation required specialized machinery and skilled labor to ensure each panel was correctly aligned and sealed to prevent leaks and improve thermal insulation. Wind tunnel testing was conducted to analyze the impact of wind loads on the towers. Based on these studies, engineers implemented tuned mass dampers within the structures. These devices counteract the swaying motion caused by high winds, providing stability and comfort for the building's occupants. But we have to travel to France next, where the LGV Sud Europe Atlantique project represents a major leap in the country's high-speed rail network. Initiated in 2011 and completed in 2017, it extends the existing high-speed line from Tours to Bordeaux. Spanning approximately 188 miles, this new section of the line significantly reduces travel times, cutting the journey from Paris to Bordeaux to just over 2 hours. One of the most impressive aspects of the LGV project is the scale of its construction. With an investment of around $8 billion, the project involved extensive engineering work, including the construction of over 400 engineering structures such as viaducts, bridges, and tunnels. The route traverses diverse landscapes, from rolling countryside to urban areas, necessitating innovative solutions to minimize environmental impact and disruption to local communities. A notable feature of the LGV line is its advanced rail technology. The line supports trains traveling at speeds of up to 200 miles per hour, making it one of the fastest rail lines in Europe. This high-speed capability is achieved through the use of state-of-the-art track design and cutting-edge signaling systems, ensuring both speed and safety. The environmental considerations of the project were paramount. Extensive environmental impact assessments were conducted, and measures were taken to protect local wildlife and natural habitats. Additionally, the project included reforestation initiatives and the restoration of natural landscapes affected by the construction. Beyond its engineering feats, the LGV project has had a profound socio-economic impact. By dramatically reducing travel times, it has enhanced the accessibility of southwestern France, promoting regional development and economic growth. The construction phase of the project provided a significant boost to the local economy, generating thousands of jobs and supporting numerous businesses. But what about the construction of a gigantic port? The London Gateway Port, strategically positioned on the north bank of the River Thames, is the United Kingdom's premier deep-sea port and Europe's most advanced logistics hub. Opened in 2013, this sprawling facility covers over 1,500 acres, equivalent to more than 1,000 football fields. It boasts 6 deep-water berths and has the capacity to handle the world's largest container ships, which can carry up to 18,000 containers each. This capability is crucial in accommodating the ever-increasing size of global shipping vessels and maintaining the UK's competitive edge in international trade. The construction of London Gateway involved over 10,000 workers at peak times, drawing on a range of specialties from marine construction to high-tech automation. The port utilizes some of the most advanced cranes and automated stacking cranes in the world, all designed to minimize cargo handling times and maximize efficiency. One of the significant challenges faced during the construction was maintaining strict environmental regulations. The project included creating a new 1,500-acre wildlife reserve as part of its commitment to biodiversity, which serves as a habitat for birdlife and other species, thereby balancing industrial development with environmental conservation. The economic implications of London Gateway are profound. A special feature of the port is its ability to function as a tidal port, which maximizes accessibility for shipping regardless of tidal movements. This feature is crucial for maintaining constant flow in operation, distinguishing it from other ports that may face operational delays due to tidal constraints. The investment in London Gateway Port of $1.87 billion mirrors the financial commitment seen in projects like the expansion of Barcelona's El Prat Airport, another critical infrastructure aimed at boosting capacity and economic growth. We have to travel over to Austria for our next project. The Koralm Tunnel is one of the most ambitious railway infrastructure projects in Europe. This 20-mile-long tunnel, part of the Koralm Railway, will connect the cities of Graz and Klagenfurt, significantly reducing travel time and enhancing connectivity in the region. The tunnel passes through the Eastern Alps, making its construction a remarkable engineering feat. Construction of the Koralm Tunnel began in 2008, with completion expected by 2026. The project involves a substantial investment, estimated at around $5.4 billion. One of the primary challenges has been tunneling through the complex geological conditions of the Alps, which requires advanced tunneling techniques and machinery. The tunnel will feature twin tubes, each with a diameter of around 30 feet, allowing for separate tracks for trains traveling in opposite directions. The design includes state-of-the-art safety systems, such as emergency exits, ventilation systems, and fire protection measures. These features are essential to ensure the safety and reliability of the tunnel, given its length and the volume of traffic it will handle. The construction of the Koralm Tunnel involves the use of tunnel boring machines, which are capable of excavating through rock and soil with precision. The machines are equipped with cutting-edge technology to manage the challenges posed by the varying geological conditions. The project also includes the construction of access tunnels, ventilation shafts, and support structures to facilitate the excavation and operation of the main tunnels. Once completed, the tunnel will reduce travel time between Graz and Klagenfurt to just 45 minutes, compared to the current 3-hour journey by car. Next up, it's time to shift our focus to Italy and delve into the ambitious Terzo Valico dei Giovi project. Located in the northwestern region of Italy, this high-speed rail line is designed to connect the city of Genoa with the broader European network, significantly improving freight and passenger transport across the region. The project began construction in 2013 and is expected to be completed by 2026. This project is part of the broader Trans-European Transport Network, which aims to integrate European rail systems and boost economic growth by improving transportation efficiency. The total investment for this project is estimated at over $7 billion. The new rail line will stretch approximately 33 miles, featuring a series of tunnels that make up over 70% of the route. These tunnels, including the Valico Tunnel, which alone spans 17 miles, are designed to traverse the rugged Apennine Mountains, reducing travel times and creating a more direct route between Genoa and the Po Valley. Constructing these tunnels has presented significant engineering challenges. The project involves boring through complex geological formations, which require advanced drilling techniques and meticulous planning. Tunnel boring machines are being used to ensure precision and safety, cutting through rock while minimizing disruption to the surface above. One of the project's primary goals is to enhance freight transport between the port of Genoa and northern Italy, as well as other European destinations. The port of Genoa is one of Italy's busiest, and the Terzo Valico dei Giovi will facilitate the movement of goods by providing a faster and more efficient rail link. In addition to freight, the new rail line will significantly improve passenger travel. Currently, journeys between Genoa and Milan can take over an hour and a half by train. Once the Terzo Valico dei Giovi is operational, this travel time will be reduced to approximately 50 minutes. Let's investigate a massive nuclear plant megaproject next, called Olkiluoto Nuclear Plant Unit 3. Launched with the aim of significantly bolstering Finland's energy independence and reducing carbon emissions, the project has taken on monumental proportions in both scope and budget. Construction of Olkiluoto 3 began in 2005, with the initial goal of completion by 2009. However, a series of technical challenges, regulatory hurdles, and construction delays pushed its anticipated operational start to 2023. The reactor is of the European pressurized reactor type, which is among the most advanced and safest nuclear reactor designs available, incorporating a multitude of redundant safety systems and modern technology to enhance its operational efficiency and safety. This unit alone adds about 1,600 megawatts of capacity to Finland's power grid, enough to power roughly 1.3 million homes. The technical complexities of building a reactor of this sophistication have necessitated innovations in construction methods, including the use of massive concrete pours that ensure the reactor's durability and resistance to any external shocks. One of the notable features of the Olkiluoto 3 project is its containment building, designed to withstand extreme external events like aircraft impacts and natural disasters, setting a new standard in nuclear safety. The volume of concrete and steel used in this project is staggering, with the containment building alone using steel reinforcement that could stretch from Helsinki to Stockholm if laid end-to-end. Financially, Olkiluoto 3 has been a behemoth, with costs escalating to an estimated $12 billion. This figure places it among the most expensive energy projects in the world, not just for its sheer scale, but also for the complexity and pioneering technology it embodies. Each delay in the timeline not only added to the cost, but also served as a lesson in international engineering projects' complexity, especially in an industry as regulated and safety-focused as nuclear power. Let's travel over to Germany now, where the Kurlbrand Bridge is undergoing a major infrastructure project aimed at replacing the existing bridge. The new bridge will connect the port of Hamburg with the city's road network, providing a critical transport link. Construction of the new Kurlbrand Bridge began in 2020, with completion expected by 2025. The project represents a substantial investment, estimated at around $1.5 billion. The new bridge will feature a main span of 325 meters, making it one of the longest cable-stayed bridges in Germany. The foundation work for the Kurlbrand Bridge required extensive geotechnical analysis to determine the optimal locations for the deep piles. Large diameter piles were driven deep into the riverbed to provide the necessary support for the bridge's massive structure. These piles were made of reinforced concrete, designed to withstand the substantial loads and dynamic forces exerted by the bridge and traffic. One notable construction technique used in the project is the incremental launching method for the bridge deck. This method involves constructing the bridge deck in sections on the shore, and then incrementally launching these sections over the piers using hydraulic jacks. This technique reduces the need for extensive scaffolding and minimizes the environmental impact on the river. The precise alignment and connection of each deck section required meticulous planning and execution. The bridge's cable-stayed design features high-strength steel cables anchored to the bridge deck and pylons. Installing these cables involved using specialized cranes and tensioning equipment to ensure the correct load distribution. The pylons, constructed using slip-forming techniques, rise majestically above the river, providing both structural support and aesthetic appeal. Managing construction activities while maintaining traffic flow on the existing bridge posed a significant challenge. To minimize disruption, the project team implemented a phased construction approach. Sections of the new bridge were completed and opened to traffic in stages, allowing continuous use of the old bridge until the new one was fully operational. The construction of the Kurlbrand Bridge exemplifies modern engineering and construction techniques, blending innovative methods with sustainable practices. Let's explore the Pont de Normandie in France, a marvel of modern engineering that elegantly spans the Seine River, connecting the cities of Le Havre and Honfleur. This iconic bridge, completed in 1995, stands as one of the longest cable-stayed bridges in the world. The Pont de Normandie stretches an impressive 7,032 feet, or approximately 1.33 miles. Its most striking feature is its central span, which measures 2,808 feet, supported by two soaring pylons that rise 656 feet above the Seine. These pylons, constructed from reinforced concrete, are designed to withstand strong winds and seismic activity, ensuring the bridge's stability and longevity. Construction of the Pont de Normandie began in 1988 and took 7 years to complete. The project was a significant undertaking, costing around $465 million. One of the engineering highlights of the Pont de Normandie is its use of cable-stayed technology, which allows for longer spans and greater flexibility compared to traditional suspension bridges. The bridge's deck is supported by a series of cables that fan out from the pylons, creating a visually stunning and structurally efficient design. The bridge's roadway consists of 4 lanes, 2 in each direction. The bridge has reduced travel time between Le Havre and Honfleur to just a few minutes, enhancing economic activities and fostering closer ties between the two cities. Architecturally, the Pont de Normandie is celebrated for its elegant and minimalist design, which complements the surrounding landscape. Its sleek lines and towering pylons make it a landmark that is both functional and aesthetically pleasing. The bridge has won numerous awards for its design and engineering, including the Outstanding Structure Award from the International Association for Bridge and Structural Engineering in 1995. The construction of the Pont de Normandie involved innovative techniques and meticulous planning. Engineers had to address several challenges, including the strong winds typical of the region and the need to maintain river traffic during construction. The use of precast concrete segments assembled on site allowed for precise construction and minimized disruptions. Each segment, weighing up to 200 tons, was carefully positioned and secured, ensuring the structural integrity of the bridge. The economic impact of the Pont de Normandie extends beyond improved transport links. It has become a tourist attraction in its own right, drawing visitors who marvel at its design and the panoramic views it offers. Moreover, the Pont de Normandie has played a vital role in regional integration within the European Union. By improving transport links between France and its northern neighbors, The bridge facilitates smoother and more efficient movement of goods and people across borders. But how about a barrier megaproject that will protect an entire city? Venice, a city renowned for its unique architecture and intricate waterways, has been facing an existential threat from flooding due to rising sea levels and sinking foundations. In response, Italy embarked on one of the most ambitious and technically complex engineering projects in Europe, the Venice Flood Barrier, officially known as the MOST project. Initiated in 2003, the project comprises a series of 78 mobile underwater gates designed to temporarily isolate the Venetian lagoon from the Adriatic Sea during high tides. Spanning 3 inlets that connect the lagoon to the sea, each gate measures 20 meters wide and weighs up to 300 tons. When not in use, these gates rest in caissons on the seafloor filled with water. During high tides, air is pumped into these caissons, causing the gates to rise and block the incoming water. The technical challenges of constructing such a system were immense. Engineers had to develop new materials and methods to ensure the gates could withstand the harsh marine environment, including building special corrosion-resistant barriers that could endure for decades. The project also involved massive dredging operations to lay the foundations of the gates, moving millions of cubic meters of seabed. But besides those challenges, delays and cost overruns were frequent as well, pushing the project's completion date several times. The initial budget ballooned from an estimated $1.6 billion to an eventual total of $5.7 billion, making it one of the most expensive megaprojects in Europe. Unlike conventional dams or levees, the Venice Flood Barrier is designed to be both invisible and temporary, appearing only when needed to protect the historic city. We have to move over to Finland next for the Hanhikivi 1 nuclear power plant. Located in Pajajoki, the project involves the construction of a new nuclear reactor, which will provide a stable and reliable source of electricity for the region. Construction of the Hanhikivi 1 nuclear power plant began in 2015, with completion expected by 2029. The project represents a substantial investment, estimated at around $7 billion. The plant will feature a Russian-designed Viver 1A200 reactor, which is known for its high safety standards and efficiency. The reactor will have a capacity of 1A200 megawatts, enough to power around 1 million homes. One of the primary challenges of the Hanhikivi 1 project has been ensuring compliance with Finland's stringent nuclear safety regulations. The project team has worked closely with regulatory authorities to ensure that the plant meets all safety requirements and is constructed to the highest standards. This includes rigorous testing and quality control measures throughout the construction process. The Hanhikivi 1 nuclear power plant will incorporate advanced safety features, such as a double containment structure, an emergency core cooling system, and a passive heat removal system. These features are designed to ensure the safety of the plant and its surrounding areas in the event of an emergency. The project also includes extensive environmental monitoring and mitigation measures to protect the local ecosystem. Nuclear power is a low-carbon energy source, and the plant will play a crucial role in helping Finland achieve its climate goals. By providing a reliable and stable source of electricity, the plant will reduce the country's dependence on fossil fuels and contribute to the reduction of greenhouse gas emissions. The construction of the Hanhikivi 1 nuclear power plant involves the use of advanced engineering and construction techniques. The project team has employed state-of-the-art technology to manage the complex logistics of building a nuclear power plant, including the transport and installation of large and heavy components. It's time to talk about one of Europe's most ambitious and delayed infrastructure projects, Berlin-Brandenburg Airport, located in Germany. The idea for this aviation hub was conceived in early 1990 after the reunification of Germany. The goal was to create a single, state-of-the-art airport that would consolidate air traffic and replace the aging Tegel and Schönefeld airports. Construction began in 2006, and the project was initially scheduled for completion in 2011. However, a series of technical problems, planning errors, and safety issues delayed the opening until October 31, 2020. The total cost of Berlin-Brandenburg Airport soared to approximately $7 billion, far exceeding the original budget of around $2 billion. The airport spans a massive area of almost 14 square miles, highlighting the scale of this undertaking. One of the most significant challenges faced during the construction of Brandenburg Airport was the complex fire safety system. The automated smoke extraction system failed numerous tests, leading to extensive redesigns and delays. Additionally, issues with wiring, escalators, and security systems required significant rework and contributed to the extended timeline. The airport features 3 terminals and 2 parallel runways, designed to handle up to 46 million passengers annually. The airport's design incorporates modern architecture with extensive use of glass and steel, providing a bright and open atmosphere for travelers. The facility includes numerous energy-efficient features, such as LED lighting, a sophisticated waste management system, and extensive use of renewable energy sources. Solar panels installed on the roof of the terminals generate a portion of the airport's electricity, reducing its environmental footprint. Despite the numerous setbacks, the airport's eventual opening has been a significant milestone. The airport now serves as a major hub for both domestic and international flights, boosting connectivity for the German capital. We travel to France next for a gigantic canal megaproject called the Seine-Nord-Europe Canal. Designed to connect the Oise River at Campigny to the Dunkirk-Escaut Canal near Cambrai, this ambitious canal extends over 107 kilometers, providing a high-capacity waterway link between Paris and major northern European ports. Slated for completion in 2028, the canal aims to alleviate road and rail congestion by providing an eco-friendlier option for cargo transport. The canal is expected to support vessels up to 400 tons, double the capacity of most existing barges in the region. This increase not only maximizes cargo volumes, but also drastically reduces the environmental impact per ton of goods transported, aligning with broader European sustainability goals. The construction of the canal involves extensive earthworks, with an estimated 50 million cubic meters of soil to be excavated. This volume of soil is enough to fill the Great Pyramid of Giza approximately 5 times over. Furthermore, the project will include the construction of 3 massive locks, each capable of lifting vessels up to 13 meters high, akin to navigating a 4-story building vertically through water. In addition to the primary waterway, the project includes the creation of 55 structures, including aqueducts and bridges, to maintain the cross-connections between divided regions and to ensure that local ecosystems and communities remain intact. The workforce on this project is tasked not only with the physical construction, but also with implementing advanced hydroengineering techniques to manage the water flow and ensure safety during the canal's operation. One of the most innovative aspects of the Seine-Nord-Europe Canal is its incorporation of smart technology. The canal will feature automated lock systems and remote-operated bridges, enhancing operational efficiency and safety. This technological integration positions the canal as a future-proof infrastructure, ready to handle the anticipated increase in automated and digital shipping processes. With a total cost of $5 billion, the Seine-Nord-Europe Canal is comparable in ambition and budget to other major infrastructure projects like London's Crossrail project. But we have to talk about the construction of Terminal 3 at Frankfurt International Airport. The new terminal, designed by the architectural firm GMP, will incorporate state-of-the-art technology and modern design elements to create a world-class facility. It will feature 3 piers, each equipped with numerous boarding gates, lounges, and retail spaces. The terminal's design emphasizes sustainability and energy efficiency, with extensive use of natural light, energy-saving systems, and environmentally friendly materials. Construction of Terminal 3 began in 2015, with the project reaching completion in 2023. The terminal represents a significant investment, estimated at around $4.5 billion. One of the primary challenges has been managing construction activities while maintaining normal airport operations. The project team has implemented advanced construction techniques and rigorous planning to ensure minimal disruption to daily operations. Terminal 3 is designed to enhance passenger comfort and convenience. The spacious terminal will offer a variety of amenities, including dining options, shopping areas, and relaxation zones. High-speed internet, comfortable seating, and abundant charging stations will cater to the needs of modern travelers. The terminal will also feature advanced security and check-in systems to streamline the passenger experience and reduce wait times. The construction of Terminal 3 involves the use of innovative building techniques, such as prefabrication and modular construction. These methods allow for faster construction times and reduced environmental impact. The project team has also employed advanced project management software to coordinate activities and ensure that the project stays on schedule and within budget. Let's dive into the impressive Afsluitdijk project in the Netherlands. Originally completed in 1932, it stretches 32 kilometers across the Wadden Sea, connecting the provinces of North Holland and Friesland. It has served as a critical barrier against the North Sea, protecting the low-lying regions of the Netherlands from flooding. The current project to upgrade the Afsluitdijk began in 2018 and was completed in 2023. This renovation is essential to cope with rising sea levels and the increasing frequency of severe weather events. The cost of the project is estimated at around €550 million, reflecting the complexity and scale of the endeavor. A significant aspect of the project is the reinforcement of the dike itself. The existing structure, which has protected the Netherlands for nearly a century, is being upgraded with the installation of innovative flood defense systems. One of the key features is the addition of new sluices and pumps to manage water levels more effectively. These systems are designed to handle excess water during storms and high tides, ensuring the safety of the surrounding areas. The project also includes the construction of a new storm surge barrier. This barrier, located at the western end of the dike, will provide additional protection against the increasingly severe storms that the region faces. The barrier is designed to be both functional and visually striking, blending seamlessly with the surrounding landscape while offering robust protection against the sea. Sustainability is a core focus of the Afsluitdijk project. The renovation incorporates renewable energy sources with solar panels and wind turbines installed along the dike to generate clean energy. These installations are expected to produce enough electricity to power the new sluices and pumps, making the Afsluitdijk not only a protective structure but also a contributor to the country's green energy goals. But what about the most expensive megaproject located in Europe? High Speed 2 is poised to be one of the most transformative rail projects in European history, designed to connect London with the north of England and potentially the central belt of Scotland. The project's primary objective is to enhance connectivity, reduce travel times between major cities, and alleviate congestion on the UK's existing rail network. Initiated with the intention to drastically reduce travel times, HS2 will see trains operating at speeds of up to 250 miles per hour. Upon its anticipated completion, the journey from London to Birmingham will be cut to just 45 minutes, compared to the current duration of an hour and 20 minutes. The project will lay down hundreds of miles of track, which requires the excavation and movement of millions of tons of earth. The project's scale is mirrored by its workforce requirements, with tens of thousands of jobs expected to be created during construction. Additionally, HS2 is a catalyst for technology and innovation in construction, employing advanced techniques in tunneling, bridging, and environmental conservation. The trains are planned to be powered by zero-carbon energy from day one of operations, aligning with the UK's broader environmental goals. The new rail lines themselves are designed to integrate with the natural landscape, incorporating green tunnels and wildlife crossings to minimize the environmental impact. However, HS2 has faced considerable problems and controversies, particularly regarding its cost and the environmental impact of its construction. With its budget now revised to an estimated $130 billion, HS2 ranks as the most expensive infrastructure project undertaken in Europe. This investment underscores the UK government's commitment to revolutionizing transport, but has also sparked debates on fiscal responsibility and environmental stewardship. Despite these challenges, the potential benefits of HS2 are substantial. It is expected to double the number of seats available out of London Euston, reducing road congestion. Let's talk about the Johan Sverdrup oil field in Norway next. Located approximately 87 miles west of Stavanger, the project involves the construction of multiple offshore platforms, pipelines, and support infrastructure to extract and transport oil from the field. Development of the Johan Sverdrup oil field began in 2015, with production starting in 2019. The project represents a substantial investment, estimated at around $17 billion. The oil field has estimated reserves of 2.7 billion barrels of oil equivalent, making it one of the most significant discoveries in the North Sea in recent decades. The construction of the Johan Sverdrup oil field required advanced engineering and construction techniques to address the challenges of operating in the harsh and unpredictable North Sea environment. The project features a network of platforms, including a processing platform, a riser platform, and a living quarters platform, all connected by bridges to create an integrated offshore complex. The foundation work for the platforms involved driving large steel piles deep into the seabed to ensure stability. Each pile was installed using specialized pile driving equipment capable of operating in deep water. The piles were then filled with concrete to enhance their load-bearing capacity and resistance to corrosion. Heavy lift vessels played a crucial role in the construction process. These vessels transported large prefabricated modules, including topsides and jackets, from fabrication yards to the installation site. The use of heavy lift vessels allowed for the efficient transport and precise placement of these massive components. Each platform was equipped with advanced drilling and processing equipment, designed to maximize efficiency and minimize downtime. The installation of pipelines to transport oil and gas from the field to onshore facilities was another critical aspect of the project. These pipelines were laid using specialized pipelay vessels, which can handle the complex seabed topography and ensure the integrity of the pipeline system. The Johan Sverdrup oil field is expected to produce oil for several decades, contributing significantly to Norway's energy production and economic growth. Let's shift our focus to Norway and delve into the fascinating Snøhvit LNG project, an ambitious energy initiative set in the Arctic region. Located in the Barents Sea, this project is Norway's first liquefied natural gas development, representing a significant leap in the country's energy capabilities. The project began with the discovery of the Snøhvit gas field in 1984. It took nearly 2 decades of planning and development before production finally commenced in 2007. This groundbreaking project is notable for its remote location and the challenges associated with Arctic conditions. One of the most remarkable aspects of the Snøhvit project is the decision to construct the LNG processing facilities onshore on Melkøya Island, near the town of Hammerfest. Natural gas extracted from the Snøhvit field is transported through a 90-mile subsea pipeline to Melkøya, where it is processed and cooled to -260 degrees Fahrenheit to be converted into liquid form. The total cost of the Snøhvit project is estimated at around $8 billion. The onshore facility on Melkøya includes Europe's largest LNG liquefaction plant, which has the capacity to produce nearly 5.7 million tons of LNG annually. This facility also includes storage tanks, loading berths, and other essential infrastructure, making it a comprehensive and self-sufficient operation. The plant on Melkøya employs cutting-edge technologies to reduce emissions and energy consumption. One notable feature is the carbon capture and storage system, which captures CO2 from the natural gas and injects it back into a reservoir beneath the seabed, preventing it from entering the atmosphere. Despite its successes, the Snøhvit project has not been without challenges. The harsh Arctic climate, with its extreme cold and long periods of darkness, poses unique operational difficulties. Ensuring the safety of workers and maintaining the integrity of equipment in such conditions require rigorous planning and robust engineering solutions. In addition to its technical achievements, Snøhvit LNG has strengthened Norway's position in the global energy market. The LNG produced at Melkøya is exported to various countries, including those in Europe and Asia, enhancing energy security and providing a cleaner alternative to coal and oil. This project has also paved the way for future Arctic developments, showcasing the feasibility and benefits of harnessing resources in remote locations. Next up, we have to look at a project that's located in between Denmark, Sweden, and Germany. The Kriegers Flak offshore wind farm stands as a towering testament to Europe's commitment to renewable energy. With 72 turbines spinning over an area of 132 square kilometers, this wind farm is a crucial step toward achieving sustainability on a grand scale. The construction of Kriegers Flak began with the dual aims of enhancing energy production and reducing carbon emissions across the region. Upon its completion in 2021, it became one of the largest offshore wind farms in the world, boasting a capacity to generate 600 megawatts of power. This is enough energy to supply approximately 600,000 households annually, significantly impacting the region's energy dependency on fossil fuels. The installation of each turbine at Kriegers Flak was a meticulous process, involving specialized ships capable of handling the enormous weight and size of the components. Each turbine reaches up to 188 meters in height, nearly as tall as the Gherkin in London. A unique feature of Kriegers Flak is its role in supporting biodiversity. Artificial reefs were created using materials from the construction to promote marine life in the Baltic Sea, showcasing an innovative approach to environmental stewardship within an industrial project. Financially, the wind farm represents a significant investment in green technology, with a total cost of $1.4 billion. This investment underscores the economic scale of transitioning to renewable energy sources, comparable in cost to constructing major infrastructure like the new Queensferry crossing in Scotland. Moreover, Kriegers Flak serves as a critical junction for power connectivity in Europe. It includes an innovative feature that allows it to serve as an interconnector between Denmark and Germany, not only generating electricity but also facilitating energy trade between countries, enhancing grid stability and supply security across borders. Let's go to Germany for the Edge East Side Tower, located in the city of Berlin. Rising to an impressive height of 140 meters, this 35-story skyscraper will serve as a mixed-use facility with both office spaces and commercial areas. One of the unique aspects of the Edge East Side Tower is its integration of cutting-edge technology to create a smart and sustainable building. The tower will feature advanced energy management systems, including solar panels integrated into the facade and smart lighting systems that adjust based on natural light availability. These systems are expected to reduce the building's energy consumption significantly, setting a new standard for green buildings in Germany. Construction of the Edge East Side Tower began in 2020, and it was completed in 2023. The project involves a substantial investment, estimated at around $400 million. The construction site is strategically located near the Warschauer Strasse station, making it easily accessible by public transport. The lobby features a spacious atrium with green walls and seating areas, providing a welcoming environment for visitors. Challenges during construction have included coordinating the installation of the advanced energy systems and ensuring that the building meets stringent sustainability criteria. The project team has employed innovative construction techniques to streamline the process, such as prefabricated components and modular construction methods. Let's embark on a journey to Norway to uncover the Nordvegen project. Spanning over 13 miles, this monumental endeavor weaves together a series of tunnels, bridges, and causeways that traverse some of the most challenging terrain in the region. The project commenced in 2017, driven by the need to enhance connectivity and improve the lives of the island residents. At its heart lies the construction of 5 tunnels, the longest of which stretches for nearly 4 miles beneath the seabed. Complementing these tunnels are several grand bridges, including the iconic Lepsoy Bridge, which arches gracefully over the treacherous waters below. Each bridge is designed not only to withstand the harsh maritime climate, but also to blend seamlessly with the stunning natural surroundings, reflecting a harmonious balance between human achievement. The scale of Nordvegen is underscored by its substantial financial commitment, with costs estimated at around $590 million. This investment reflects the project's importance to the region, promising significant economic and social benefits. Once completed, the road will drastically reduce travel times, transforming what was once a multi-hour ferry journey into a seamless drive of mere minutes. Building Nordvegen presented formidable challenges. The construction teams had to contend with the relentless forces of nature, including unpredictable weather and the powerful currents of the Norwegian Sea. The project's impact extends far beyond mere connectivity. It is set to revitalize the local economy, providing easier access for businesses and boosting tourism. The improved infrastructure will attract new opportunities and investments, fostering growth and development in these previously isolated communities. For the next project, it's time to move over to Belgium. The LNG terminal Zeebrugge is strategically positioned at the crossroads of maritime routes that link northern Europe with LNG-producing regions, including Qatar and the United States. The facility serves as a critical reception point for liquefied natural gas, which is then regasified and fed into the European gas grid. This project, initiated with an eye on the future energy landscape, features state-of-the-art technology, including LNG storage tanks and regasification units. These tanks are massive, each with a capacity to store up to 180,000 cubic meters of LNG, roughly equivalent to 72 Olympic-sized swimming pools per tank. The terminal's regasification capability stands at an impressive rate, able to process billions of cubic meters of gas annually, directly feeding into Europe's energy network. The completion of the terminal is set for 2026, aiming to address one of Europe's most pressing problems: energy dependency. By increasing the number of entry points for LNG into Europe, the terminal not only diversifies the energy supply, but also stabilizes it, making it less susceptible to geopolitical fluctuations that can affect natural gas pipelines from traditional sources. With a total investment of $1.2 billion, This project aligns with the likes of the Fehmarn Belt fixed link between Denmark and Germany. The specialty of the Zeebrugge project isn't just in its operational capabilities, but also in its design and environmental considerations. Featuring advanced vapor recovery systems, the terminal minimizes environmental impact by capturing and reliquefying gas that evaporates during operations, showcasing a commitment to sustainable practices in industrial design. Let's move over to the Netherlands next for the Rotterdam Towers megaproject. Designed by the renowned architect Rem Koolhaas, the project comprises 3 interconnected towers that rise to a height of 150 meters. Construction of the Rotterdam Towers began in 2009 and was completed in 2013. The project involved a significant investment of around $550 million. One of the unique features of the development is its innovative design, which maximizes space and functionality within a compact footprint. The towers are connected by a series of sky bridges, creating a dynamic and visually striking structure. The Rotterdam Towers project aimed to create a vibrant urban community with a mix of residential, commercial, and recreational spaces. The development includes 240 apartments, 72,000 square meters of office space, a 4-star hotel with 285 rooms, and a variety of retail and dining options. The project also features extensive public spaces, including a plaza and a rooftop garden, providing residents and visitors with green areas to relax and socialize. The construction process presented several challenges, including the need to coordinate multiple building functions within a single structure and ensure that all systems were seamlessly integrated. The project team employed advanced building information modeling technology to plan and execute the construction, allowing for precise coordination and efficient use of resources. The Rotterdam Towers have become a landmark in the city, symbolizing Rotterdam's innovative spirit and commitment to sustainable urban development. The project has received numerous awards for its design and sustainability features, highlighting its significance as a model for future urban developments. But what about the construction of the biggest train station in the Netherlands? Utrecht Central Station, originally built in 1930, has long been a crucial node in the Dutch railway network. With over 200,000 passengers passing through daily, it became evident that the station required a significant upgrade to meet modern demands. The redevelopment project, initiated in early 2000 and completed in 2016, represents a blend of innovative design and practical enhancements. The station's transformation involved a substantial investment of around $1 billion, underscoring its importance to the national transport network. The project focused on expanding capacity, improving passenger flow, and integrating various modes of transportation. A key feature of the redevelopment was the construction of a new, expansive station hall. This hall, characterized by its sleek, modern design and extensive use of glass, provides a bright and welcoming space for travelers. The new station includes widened platforms and additional tracks to accommodate more trains, reducing delays and improving efficiency. Sustainability was a cornerstone of the Utrecht Central Station redevelopment. The project incorporated numerous eco-friendly features, such as energy-efficient lighting, solar panels, and advanced climate control systems. Green roofs and rainwater harvesting systems have been implemented to reduce the station's environmental footprint. The station is now a multimodal transportation hub, integrating various forms of transport seamlessly. A new bus terminal and extensive bicycle parking facilities have been added, encouraging the use of public transport and cycling over cars. The integration of these different modes of transport not only enhances connectivity, but also supports the city's goals of reducing traffic congestion and promoting sustainable urban mobility. One of the most striking elements of the project is the Hugh Cathrany shopping mall, which connects directly to the station. This modern retail complex offers a wide range of shops, restaurants, and services, turning the station area into a vibrant commercial hub. It's time to travel to Germany, where the Rastatt Tunnel is located. This underground endeavor aims to improve the European rail network, specifically designed to alleviate the strain on existing rail routes and significantly enhance cargo and passenger travel efficiency between Karlsruhe and Basel. The Rastatt Tunnel stretches over a length of 4,270 meters, and it will end up costing around $1.2 billion. Construction kicked off in 2016, but it hasn't been without its challenges. In 2017, a significant setback occurred when part of the tunnel collapsed, causing extensive delays and requiring a reevaluation of project strategies and safety measures. Approximately 2,000 workers have been involved in this mega project, utilizing state-of-the-art construction methods such as tunnel boring machines that carve through the earth with precision. The tunnel features twin tubes, each 10 meters in diameter, which is about as wide as 3 cars parked side by side. These massive tubes are designed to handle the increased rail traffic, with an expected completion and operational date set for 2026. Material-wise, the project is a showcase of modern engineering, using thousands of tons of steel and concrete to ensure structural integrity and safety. In terms of problem solving, the tunnel is a crucial component in the larger strategy to create a more cohesive and efficient European transit network. Next up, we have to move over to the United Kingdom for the Liverpool Street Station redevelopment project. This endeavor is focused on enhancing capacity, improving accessibility, and upgrading facilities to meet the demands of increasing passenger numbers. The station, originally opened in 1874, is undergoing a significant overhaul to integrate contemporary design elements while preserving its historical character. A key feature of the redevelopment is the expansion of the station's concourse, which will increase the available space for passengers and reduce congestion during peak times. This includes the construction of new entrances, wider platforms, and additional escalators and lifts to improve the flow of people throughout the station. Sustainability is at the heart of the Liverpool Street Station redevelopment. The project includes the installation of energy-efficient lighting, water-saving fixtures, and a new waste management system designed to reduce the station's environmental footprint. The construction phase, which began in 2020, is scheduled to be completed by 2025. The redevelopment involves a substantial investment, estimated at around $1.5 billion. One of the difficult challenges of this project is maintaining station operations while construction is underway. To minimize disruption, the project team has implemented a phased construction approach, allowing sections of the station to remain open and functional throughout the redevelopment process. Another critical aspect of the redevelopment is the integration of Liverpool Street Station with the Elizabeth Line. This integration will provide seamless connections to other parts of London and improve travel times for commuters. The new concourse will connect directly to the Elizabeth Line platforms, enhancing accessibility and making it easier for passengers to navigate between different transport services. Let's journey to Norway to explore the remarkable Follow Line project. This megaproject is an essential part of the inner-city triangle, which aims to improve transportation efficiency across the eastern part of Norway. The project began construction in 2015 and opened up to the public in 2022. This new railway line stretches over 22 kilometers and includes the longest railway tunnel in Scandinavia, measuring 19 kilometers. The entire project comes with a hefty price tag of around $2.4 billion, reflecting its vast scale and the cutting-edge technology employed. One of the most ambitious aspects of the Follow Line is its twin tunnel system. Bored through solid rock, these parallel tunnels will drastically reduce travel time between Oslo and Ski, cutting it down to just 11 minutes from the previous 22. The construction of these tunnels involved the use of 4 state-of-the-art tunnel boring machines, each named after historical Norwegian women. These colossal machines, each over 150 meters long, worked simultaneously to excavate the tunnels. A notable engineering challenge of the Follow Line project was the need to navigate through complex geological conditions, including hard gneiss rock and sections of softer ground. Advanced ground freezing techniques were employed in some areas to stabilize the ground, ensuring the safety and stability of the tunnels during excavation. In addition to the tunnels, the Follow Line includes the construction of new stations and upgrades to existing infrastructure. The new ski station is designed to handle increased passenger volumes and will feature modern amenities, including expanded platforms and improved accessibility. These upgrades are expected to accommodate the projected rise in passenger numbers, making train travel more convenient and attractive. Let's travel to the United Kingdom next for the Hinkley Point C Power Station. This project, which broke ground in 2016, aims to provide a secure, low-carbon energy source capable of powering approximately 6 million homes. The Hinkley Point C project is the first new nuclear power station to be built in the UK in over 20 years. Upon completion, it will house 2 European pressurized reactors, each expected to deliver 1,630 megawatts of power. The significance of this development extends beyond energy generation. It's a critical move towards sustainable industrial growth and job creation. The construction of Hinkley Point C has brought together a workforce of around 25,000 over its lifespan. The project site spans 430 acres, and the volume of concrete to be used in the construction is projected to be enough to fill 75 football stadiums. Technologically, Hinkley Point C employs advanced safety and operational features, including a robust cooling system and state-of-the-art security measures to ensure safe, continuous operation. The design also incorporates lessons learned from previous nuclear developments, making it one of the safest and most efficient nuclear power plants globally. Challenges faced during the project have been substantial. These include regulatory hurdles, financial negotiations, and public opposition based on safety concerns. Moreover, the project's timeline has been impacted by the intricate nature of nuclear construction and the need for rigorous inspection and quality control to meet stringent nuclear safety standards. Economically, the investment in Hinkley Point C is significant, with costs estimated at around $43 billion. This makes it one of the most expensive energy projects ever undertaken, comparable in cost to the creation of vast urban developments. Hinkley Point C's strategic importance is underscored by its projected output, which will provide about 7% of the UK's total electricity needs with reliable, low-carbon energy. This is crucial for a country aiming to phase out coal by 2024 and reduce greenhouse gas emissions significantly by 2050. It's time to investigate the Pont de Saint-Nazaire in France, which is a major infrastructure project focused on improving transport connectivity across the Loire River. Construction of this new cable-stayed bridge began in 2015, with completion achieved in 2023. The project, estimated at around $600 million, aims to replace the existing bridge and handle increasing traffic volumes. To begin, extensive foundation work was required to support the new bridge's structure. Engineers used deep drilling techniques to install large-diameter piles deep into the riverbed, ensuring stability and load-bearing capacity. These piles were constructed using reinforced concrete, capable of withstanding the considerable weight and dynamic forces exerted by the bridge and traffic. The bridge features a main span of 404 meters, making it one of the longest cable-stayed bridges in France. Construction involved assembling massive steel girders and precast concrete segments, which were transported to the site and lifted into place using high-capacity cranes. The precision alignment of these segments was critical to ensure the structural integrity and smooth curvature of the bridge. Cable installation was another key phase. The stay cables, made of high-strength steel, were anchored to the bridge deck and pylons. Tensioning these cables required meticulous calibration to balance the load distribution across the bridge. Engineers used hydraulic jacks to apply the necessary tension, carefully monitoring the stresses to prevent any structural imbalances. Managing construction activities while maintaining traffic flow on the existing bridge posed a significant challenge. To minimize disruption, a phased construction approach was implemented. Sections of the new bridge were completed and opened to traffic in stages, allowing continuous use of the old bridge until the new one was fully operational. This approach demanded precise scheduling and coordination to ensure safety and efficiency. The construction of the Pont de Saint-Nazaire exemplifies modern engineering and construction techniques, blending innovative methods with sustainable practices. But what about the Puente de Ran project, located in Spain? This iconic bridge, integral to the region's infrastructure, not only facilitates efficient transportation, but also stands as a symbol of modern engineering. Constructed in 1978 and expanded significantly in recent years, the Puente de Ran connects the city of Vigo with the Marazzo Peninsula, playing a critical role in the AP9 highway. The original bridge was designed by Italian engineer Fabrizio de Miranda, known for his expertise in long-span bridges. It stretches over 1.1 miles, making it one of the longest bridges in Spain. The expansion project, initiated in 2015 and completed in 2018, was driven by the need to alleviate traffic congestion and improve safety. The upgrade involved the addition of 2 new lanes, increasing the bridge's capacity to 6 lanes. This expansion was a challenging engineering feat, requiring precise planning and execution to ensure the bridge remained operational throughout the construction process. The project cost approximately $191 million, reflecting the complexity and scale of the undertaking. One of the standout features of the expansion was the use of innovative construction techniques, such as the installation of new decks alongside the existing structure without closing the bridge to traffic. This approach minimized disruption and showcased the ingenuity of modern bridge engineering. The Puente de Ran serves as a vital link for the region's economy. By improving the connectivity between Vigo, one of Spain's busiest ports, and the surrounding areas, the bridge supports local industries, including shipbuilding, fishing, and tourism. It's time to go to Germany next, where Stuttgart 21 is being constructed. This project is a visionary rail and urban development project that fundamentally transforms Stuttgart's transport infrastructure and urban landscape. Initiated with construction in 2010, Stuttgart 21 is one of the most complex rail projects in Europe. It involves the excavation of 57 kilometers of new tunnels and the construction of 25 kilometers of new rail lines. The scale of earth moved in this project is staggering enough to fill several thousand Olympic-sized swimming pools. This involves intricate engineering to handle and dispose of materials while ensuring stability for new and existing structures. Additionally, the project includes the redevelopment of 100 hectares of land in the city center, which will provide space for new homes, parks, and commercial areas once the rail lines are underground. The project has faced numerous challenges since its inception, including public protests and escalating costs. Originally estimated at around $4.5 billion, the budget has since ballooned to approximately $9.8 billion, making it one of the most expensive infrastructure projects in Europe. The increase in costs and the time required to manage such a massive undertaking have been points of contention and public debate. Despite these challenges, the benefits of Stuttgart 21 are projected to be significant. The new station will reduce travel times, increase train capacity, and improve connectivity between Stuttgart and major European cities. It's expected to enhance local and regional economic development and reduce traffic congestion in Stuttgart's city center. Approximately 5,000 workers are involved in this project, employing cutting-edge construction techniques and technologies. For instance, the use of slab track, a type of railway track that provides a consistent and stable base, is a key feature in modernizing the railway system. Comparatively, the total cost of $9.8 billion reflects a financial scale similar to that of constructing the new Terminal 5 at London's Heathrow Airport, underscoring the significant investment required for state-of-the-art infrastructure projects. Let's move over to the Netherlands next for the highly impressive North-South Line metro project. The new metro line, which runs from the northern to the southern parts of Amsterdam, provides a fast and efficient transport option for residents and visitors. The project involved the construction of new tunnels, stations, and tracks, significantly enhancing the city's transport network. Construction of the North-South Line began in 2002, with completion achieved in 2018. The project represents a substantial investment, estimated at around $3.1 billion. One of the primary challenges of the project was tunneling through the soft and waterlogged soil of Amsterdam, which required advanced engineering techniques and machinery. The North-South Line features 9 new stations, each designed with modern amenities and advanced technology. Sustainability is a key focus of the North-South Line project. The new metro line is powered by renewable energy, and the stations are equipped with energy-efficient systems, such as LED lighting and advanced heating and cooling technologies. One of the significant challenges of the project was maintaining the city's normal operations while construction was underway. To minimize disruption, the project team employed a phased construction approach, allowing sections of the metro line to be completed and open to the public, while work continued on other sections. This approach requires careful planning and coordination to ensure that the project stays on schedule and within budget. The North-South Line has significantly improved public transport in Amsterdam, providing a fast and reliable connection between the northern and southern parts of the city. The new metro line has reduced travel times and eased congestion on other transport routes, contributing to the overall development of the city's transport network. It's time to turn our attention to the Netherlands and explore the ambitious Zuiderzee project, a major infrastructure initiative set to transform Amsterdam's bustling Zuiderzee district. Initiated in 2019, the project is a multifaceted endeavor aimed at upgrading the existing infrastructure in the district. With a budget of around $2 billion, this project reflects the strategic importance of Zuiderzee as a center for finance, law, and business. The project is scheduled for completion by 2028, promising to deliver significant benefits to the area and its residents. At the core of the Zuiderzee project is the expansion and modernization of Amsterdam Zuid Station, transforming it into a major transportation hub. The station will be upgraded to accommodate increased passenger volumes and to improve connectivity with other parts of the city and the region. This includes the addition of new platforms, enhanced facilities, and better accessibility, making it a central node in Amsterdam's transportation network. Another key component of the project is the widening of the A10 South Ring Road. This section of the highway, which currently experiences heavy congestion, will be expanded to improve traffic flow and reduce travel times. The construction of new tunnels will allow the highway to pass underground in certain sections, freeing up surface space for urban development and green areas. These tunnels are designed to integrate seamlessly with the existing road network, minimizing disruption while enhancing capacity. Additionally, smart traffic management systems will be implemented to optimize traffic flow and reduce congestion, making transportation in and around Zuidas more efficient and sustainable. It's time to move over to Switzerland for an incredibly expansive collider project. The Large Hadron Collider, straddling the Swiss-French border near Geneva, represents one of the most audacious experiments in the history of science. With a project cost of $4.75 billion, this behemoth is not only the world's largest particle accelerator, but also a centerpiece in our quest to unravel the mysteries of the universe. Envision a circular tunnel 27 kilometers in circumference, buried up to 175 meters underground. This isn't just any tunnel, it's a superhighway where protons travel at nearly the speed of light, colliding 600 million times per second. These collisions generate temperatures 1 million times hotter than the center of the sun, momentarily recreating the conditions of the universe a fraction of a second after the Big Bang. The project's construction required the precision of aligning its two beams to within a hair's breadth over its 27-kilometer length. The magnets used to steer the beams are superconducting and must be cooled to -271.3 degrees Celsius. In 2012, the collider proved its worth by confirming the existence of the Higgs boson, often called the God particle. This elusive particle, key to the theory that explains how other particles get their mass, had remained only a theory for nearly 50 years until the collider's experiments confirmed it. But the Large Hadron Collider isn't just about particle physics. It's a hub of innovation that's propelled advances in fields like medical imaging and computing. For instance, technologies developed at CERN have led to improvements in PET scans, a crucial medical diagnostic tool. Let's travel to Switzerland for the next project on our list, the Stade de la Tuilière. Located in the city of Lausanne, the stadium is part of a larger sports complex that includes training facilities, a sports academy, and recreational areas. The project aims to provide a modern and comfortable environment for athletes and spectators, enhancing the city's sports infrastructure. Construction of the Stade de la Tuilière began in 2018 and was completed in 2020. The project represents a significant investment, estimated at around $80 million. The stadium has a seating capacity of 12,000, with the possibility of expanding to 15,000 in the future. The design of the stadium emphasizes visibility and comfort, with unobstructed views from every seat and ample facilities for spectators. One of the unique features of the Stade de la Tuilière is its modular design, which allows for flexibility in its use and configuration. The stadium can be adapted to host a variety of events, including concerts, community events, and other sports competitions. This flexibility is achieved through the use of retractable seating and movable partitions, which can be adjusted to create different seating arrangements and field configurations. The stadium is equipped with advanced technology to enhance the spectator experience. This includes high-definition video screens, a state-of-the-art sound system, and extensive lighting to ensure excellent visibility for both day and night events. The Stade de la Tuilière has quickly become a landmark in Lausanne, providing a modern and versatile venue for sports and entertainment. Let's head to France to explore the Flamanville nuclear reactor project. Located in the Normandy region, the Flamanville 3 reactor is part of the larger Flamanville nuclear power plant, which already includes 2 operational reactors. Construction on the Flamanville 3 reactor began in 2007. This project is a flagship for the European pressurized reactor technology, developed by Framatome and Électricité de France. The EPR is an advanced design aimed at increasing efficiency and safety in nuclear power generation. However, the road to completion has been anything but smooth. Originally slated to be operational by 2012, the project has encountered numerous delays and cost overruns. The estimated cost of Flamanville 3 has ballooned from an initial $3.3 billion to over $13 billion. This makes it one of the most expensive nuclear projects in Europe. The delays have primarily been due to stringent safety requirements, technical challenges, and regulatory changes, each adding layers of complexity to an already intricate project. Flamanville 3 is designed to generate approximately 1,630 megawatts of electricity, enough to power about 1.5 million homes. The reactor utilizes EPR technology, which features a double-layered containment structure to prevent radiation leaks and a core catcher to contain the reactor core in the event of a meltdown. One of the major engineering challenges of the Flamanville 3 project has been the quality control of materials and construction. For example, in 2015, it was discovered that some of the steel components in the reactor vessel had higher carbon content than specified, potentially affecting their strength and safety. This required extensive testing and, in some cases, replacement of parts, further delaying the project. Despite these setbacks, significant progress has been made. The reactor building, towering over 200 feet high, houses the most advanced nuclear technology available. The control room is equipped with cutting-edge systems to monitor and manage reactor operations in real time, ensuring the highest standards of operational safety. The project is now estimated to be completed by mid-2024. It's time to investigate the London Array offshore wind farm next. This colossal project, operational since 2013, spans an area of 100 square kilometers, roughly the size of 14 football fields, making it one of the largest offshore wind farms in the world. Comprising 175 turbines, each towering up to 147 meters high, the London Array has a peak capacity of 630 megawatts. This enormous output is capable of powering nearly 500,000 homes, significantly contributing to the IAC's renewable energy targets. The installation of turbines in a marine environment posed complex challenges, from logistical hurdles in transporting massive components by sea to installing them on the seabed amidst varying weather conditions. The project also necessitated the laying of over 200 kilometers of underwater cables that connect the turbines to each other and to the power grid onshore. Safety and environmental sustainability were paramount throughout the construction phase. Innovative measures were implemented to protect the local marine ecosystem, including the use of bubble curtains, a technique that minimizes the impact of underwater noise on marine life during pile driving activities. The scale of the London Array can be likened to that of the Hoover Dam in terms of electricity output, although the technologies and the environments they harness are vastly different. The investment of $2.35 billion into this project places it among the titans of European mega-projects. Let's talk about the incredible Genoa Bridge in Italy. Officially known as the Genova-San Giorgio Bridge, this project was initiated following the tragic collapse of the old Morandi Bridge in August 2018. Construction of the bridge commenced in April 2019 and was completed in just over a year, opening to traffic on August 3, 2020. This impressive timeline was achieved through the concerted efforts of approximately 1,000 workers who toiled around the clock. The project cost an estimated €202 million, reflecting the urgent need and the scale of the endeavor. The new bridge spans 1,067 meters in length, with a width of 31 meters. To put this into perspective, the length of the bridge is equivalent to nearly 11 football fields laid end to end. Its height varies, with the tallest piers standing at 45 meters, offering a majestic view over the Polsevera River. One of the key engineering challenges was the necessity to construct the bridge swiftly and safely, considering the urgency of replacing the collapsed structure that had severed a crucial transportation link in the region. The construction involved the use of advanced building techniques, such as prefabricated steel segments, which were assembled on site to accelerate the process. These segments were meticulously designed to fit together seamlessly, ensuring both structural integrity and aesthetic appeal. In terms of design, the bridge features a continuous steel deck supported by 14 reinforced concrete piers. Each pier is equipped with sensors and monitoring systems to ensure ongoing structural health and safety, a critical consideration given the tragic history associated with its predecessor. Sustainability was a key focus throughout the project. Next up, it's time to travel over to Norway for the Oslo Central Station project. This development involves extensive upgrades to the station's infrastructure, including the construction of new platforms, tracks, and passenger facilities. The goal is to improve capacity, accessibility, and the overall passenger experience. Construction of the Oslo Central Station redevelopment began in 2018, and it's bound to be fully operational by the end of 2024. The project represents a significant investment, estimated at around $2 billion. One of the key features of the redevelopment is the expansion of the station's concourse, which will provide more space for passengers and reduce congestion during peak times. The project includes the construction of new platforms and tracks to accommodate the increasing number of trains and passengers using the station. Additionally, the redevelopment will feature new retail and dining options, creating a vibrant and dynamic environment for travelers. One of the primary challenges of the Oslo Central Station project has been maintaining station operations while construction is underway. To minimize disruption, the project team has implemented a phased construction approach, allowing sections of the station to remain open and functional throughout the redevelopment process. This approach has required careful planning and coordination to ensure that the project stays on schedule and within budget. The improved facilities and infrastructure will support the growing number of passengers using the station and contribute to the overall development of the city's transport network. It's time to dive into Madrid Nuevo Norte, Spain's most ambitious urban development project, which promises to redefine the northern skyline of the capital city. Spanning approximately 590 acres, Madrid Nuevo Norte is designed to address the city's growing needs by creating a harmonious blend of residential, commercial, and recreational spaces. One of the most striking aspects of the project is its budget, which is estimated to be around $8 billion. At the heart of Madrid Nuevo Norte is the redevelopment of Chamartin Station, transforming it into a state-of-the-art transport hub. This upgrade will enhance connectivity by integrating high-speed trains, commuter services, and metro lines, making it one of the most important transportation nodes in Spain. The project also emphasizes sustainability, with plans to create extensive green spaces and promote environmentally friendly practices. More than 25% of the area will be dedicated to parks and open spaces, aiming to provide residents with ample recreational opportunities and improve the city's air quality. Housing is a crucial component of Madrid Nuevo Norte, with plans to build around 2,500 new homes. A significant portion of these will be affordable housing units, ensuring that the development caters to a diverse population. Next up, we have to talk about one of the most expensive electrical projects in Europe, called the Viking Link project. This is an ambitious power connection project stretching over 760 kilometers between the United Kingdom and Denmark. Its primary aim is to enhance the security and sustainability of energy supply by enabling the transfer of up to 1,400 megawatts of electricity between the two countries, enough to power approximately 1.4 million homes. Initiated in 2020, this project is pivotal in fostering energy cooperation across borders. The construction involves laying submarine and underground cables from Revsing in Denmark to Bicker Fen in Lincolnshire. These cables are engineered to withstand harsh marine environments and provide a reliable conduit for electricity over decades. The technology used in the Viking Link incorporates high-voltage direct current systems, which are more efficient over long distances than the more common alternating current systems. Addressing challenges such as environmental impact and technical complexities, the project required meticulous planning and consultation with marine biologists to minimize disruption to marine life. Additionally, engineers face the technical challenge of routing cables through varied terrains, including the North Sea's challenging seabed. The project also incorporates cutting-edge converter stations at each end, which are crucial for converting electricity between DC used in transmission and AC used in domestic power grids. With a total cost of $1.92 billion, this project represents a major investment in sustainable infrastructure. But we have to talk about the Roch Tower 2 in Switzerland. The project involves the construction of a 205-meter tall tower, which will house offices, research facilities, and conference spaces. Construction of the Roch Tower 2 began in 2018 and was finished in 2022. The foundation work for Roch Tower 2 required extensive excavation to accommodate the building's massive weight. Deep foundations were established using reinforced concrete piles driven into the ground, ensuring stability and load-bearing capacity. This phase involved careful geotechnical analysis to account for Basel soil conditions and to mitigate any potential settling issues. One of the unique construction techniques used was the top-down construction method. This involved simultaneous construction of the above-ground structure and the underground basements. The top-down approach allowed for faster progress and reduced the overall construction timeline. Large steel columns were installed first, followed by the construction of the ground-level slab. As the above-ground floors were built upwards, the underground levels were excavated and constructed downwards. The core of the tower was constructed using a slip-form method, which allows for continuous pouring of concrete. This technique ensures a seamless and strong core structure, essential for the building's stability and integrity. Slip forming involved 24/7 operations, with teams working in shifts to maintain a continuous concrete pour. The steel framework for the tower required meticulous planning and coordination. Prefabricated steel beams and columns were transported to the site and assembled using high-capacity cranes. The use of building information modeling technology was crucial during this phase, allowing for precise planning and reducing the likelihood of errors. Installing the glass facade was a complex and precise process. Each glass panel was custom-made to fit the tower's design specifications, providing thermal insulation and energy efficiency. Specialized lifting equipment was used to hoist the large glass panels into place, where they were secured and sealed. We have to talk about a massive pipeline project that crosses multiple European countries. The Trans-Adriatic Pipeline represents a groundbreaking stride in European energy infrastructure, stretching 878 kilometers from the Greek-Turkish border through Albania and into Italy. Completed in 2020, the pipeline is a key segment of the Southern Gas Corridor, a strategic initiative to reduce dependence on Russian gas by bringing new sources to European markets. The project taps into the vast gas fields of Azerbaijan, specifically the Shah Deniz field, which holds an estimated 1.2 trillion cubic meters of gas. Constructing the pipeline was a feat of engineering and environmental planning. The pipeline crosses diverse terrains and climates, from the plains of Greece to the rugged mountains of Albania and the depths of the Adriatic Sea. Each segment poses unique challenges, such as in Albania, where the pipeline ascends to an altitude of over 2,100 meters before descending to sea level, a feat akin to laying a pipeline across the height of Mount Kilimanjaro. The project navigated delicate ecosystems and densely populated areas with minimal disruption. Advanced horizontal directional drilling was used to install sections of the pipeline beneath sensitive areas, avoiding surface disturbance to habitats and human settlements. This project required an immense investment of $4.8 billion, which is a similar cost compared to the new Berlin-Brandenburg Airport. The pipeline's specialty lies in its operational technology, including state-of-the-art compressor stations in Greece and Albania that are capable of reversing flow, meaning that Europe can either receive or send gas depending on supply and demand dynamics. It's time to turn our attention to Norway and uncover the impressive Hålogaland Bridge. Completed in December 2018, this remarkable structure spans the stunning Rombeksfjord near Narvik. The Hålogaland Bridge stretches an impressive 5,381 feet. The main span alone measures 4,255 feet, making it the longest suspension bridge span in Norway and the seventh longest in Europe. The height of the bridge towers reaches an awe-inspiring 607 feet, providing the necessary support for the expansive span over the fjord. Construction of the bridge began in 2013, with a total investment of around $400 million. Prior to the bridge's completion, the journey around the fjord required a lengthy detour, adding an extra 21 miles to the trip. With the bridge in place, travel distance is cut by nearly 18 miles, saving approximately 20 minutes for drivers. The bridge was designed to withstand the harsh Arctic climate, including strong winds, heavy snowfall, and freezing temperatures. Engineers employed advanced materials and construction techniques to ensure the bridge's durability and safety. The cables supporting the bridge are made from high-strength steel, capable of bearing enormous loads while maintaining flexibility. Let's investigate the Plock-Olfen complex located in Poland next. This project involves the construction of new production units, storage facilities, and support infrastructure to enhance the complex's output and efficiency. Construction of the complex began in 2020, with it being completed in 2023. The project represents a significant investment, estimated at around $3 billion. One of the primary objectives is to increase the production of ethylene and propylene, which are essential feedstocks for the chemical industry. These products are used in the manufacturing of plastics, synthetic rubber, and other industrial materials. The complex features state-of-the-art production units equipped with advanced technology to ensure efficient and environmentally friendly operations. The project includes the construction of a new steam cracker, which will break down hydrocarbons into ethylene and propylene using high-temperature steam. This process is critical for producing the raw materials needed for various chemical products. The new facilities will incorporate energy-efficient technologies and systems to reduce emissions and minimize environmental impact. The project also includes measures to manage waste and water use, ensuring that the complex operates in an environmentally responsible manner. One of the challenges of the project has been coordinating the construction activities while ensuring the continued operation of the existing facilities at the Plock site. The project team has employed advanced project management techniques to plan and execute the construction, minimizing disruptions and ensuring that the project stays on schedule and within budget.
In an environment where minimizing disruption to major interstate corridors is paramount, the I-95 bridge replacement in Westport, Connecticut, demonstrated the full potential of accelerated bridge construction methods, specifically the lateral slide technique. This project involved replacing a structurally deficient bridge over Saugatuck Avenue, one of the busiest stretches of I-95 in the region, and doing so within a matter of days rather than months. The strategy required meticulous preparation, extensive off-site construction, and flawless execution during a very short highway closure window. The existing structure, carrying both northbound and southbound traffic, had reached the end of its service life. Deterioration in the substructure and deck made full replacement necessary, but the surrounding context, a dense suburban area with no practical detour options, meant that a traditional replacement approach was unfeasible. Engineers turned to a plan that would pre-build the new bridge spans adjacent to the existing alignment, then slide them into position during a single, carefully scheduled weekend closure of I-95. Before anything could be moved, a complex network of temporary supports, approach transitions, and hydraulic jacking systems had to be prepared. Construction crews built the new bridge structures on temporary foundations parallel to the active highway lanes. These new spans consisted of precast concrete deck panels integrated with steel girders, forming a composite superstructure. All connections, reinforcements, drainage components, and lighting conduits were pre-installed to reduce on-site finishing work after the move. While traffic continued to flow on the existing bridge, crews below worked on the new bridge's final foundation and abutment construction. These included concrete abutments supported by deep foundation systems, such as driven piles, along with bearing pads designed specifically to accept the sliding load. The horizontal slide surface was engineered using Teflon-coated pads and stainless steel slide tracks designed to minimize friction during the move. When the designated closure window arrived, the entire section of I-95 was shut down, and demolition crews moved quickly to remove the existing bridge. This required heavy excavators, saw-cutting equipment, and debris haulers working in synchronized shifts to clear the area within hours. As soon as the old structure was out of the way, hydraulic jacks were engaged to push the new bridge spans laterally onto the permanent abutments. This slide was conducted at a controlled pace, typically a few feet per hour, with continuous monitoring to ensure alignment, levelness, and bearing engagement. Once the new bridge was in place, the final phase included forming and pouring the deck closure joints, completing the approach slabs, connecting utility runs, applying waterproofing membranes, and finishing the surface paving. Precast parapets and guardrails were already attached to the new deck, eliminating the need for extensive post-move safety installations. Within just a few days, traffic was flowing again over a brand new structure with enhanced load capacity, seismic performance, and modern safety features. The I-95 bridge slide in Westport became a prime example of how advanced construction methods can be leveraged to perform full-scale bridge replacements in compressed timelines without sacrificing quality, safety, or functionality. Rising high on the Ethiopian plateau, more than 2 kilometers above sea level, Addis Ababa has always been a city of layers. Old and new, formal and informal, chaotic and alive. But over the past few years, the city has begun to take on an entirely new shape. The Addis Ababa City Corridor and Smart City Project is the centerpiece of that transformation, a sweeping plan to modernize the capital, expand its infrastructure, and create a blueprint for what a 21st century African metropolis can look like. At its heart, the project is about connection. Addis Ababa has grown rapidly, with millions of people moving in from rural regions, but the city's layout and infrastructure never quite kept pace. Roads became crowded, neighborhoods expanded without clear planning, and public services struggled to keep up. The City Corridor Plan aims to tie it all together, a network of modern boulevards, transit routes, and green corridors stretching across the city, designed to integrate housing, commerce, and technology in one continuous urban system. Think of it as both a transportation project and a digital backbone, built to link everything from the city's financial district to its emerging industrial zones. The smart city component is what makes it truly forward-looking. It's not just about widening roads or adding new buildings. It's about embedding intelligence into the fabric of the city itself. Sensor-based traffic management, integrated public data systems, and sustainable utilities that can monitor and adapt in real time. Streetlights powered by solar panels, automated waste collection, water systems that track usage and detect leaks, and transport routes that update dynamically based on congestion. All of these features form part of the vision. Addis Ababa isn't just being expanded, it's being reprogrammed. Alongside the technology, there's also a strong architectural and social vision. The new city corridors are planned to include dedicated pedestrian paths, landscaped parks, and mixed-use developments that bring homes, offices, and public spaces together. Rather than separating zones by function, the aim is to create integrated communities that reduce the need for long commutes and support more sustainable living. It's a response to the sprawl that has defined much of the city's past growth, turning what used to be dusty, disconnected suburbs into modern, connected districts. The construction itself is happening in phases, with local and international teams working together to upgrade transport corridors, build smart infrastructure, and prepare new land for development. It's a massive logistical challenge involving coordination between ministries, tech companies, and city planners, all while trying to minimize disruption in one of Africa's busiest urban centers. But despite the complexity, progress continues steadily, with visible changes appearing year by year. New roads lined with smart lighting, new districts emerging with coordinated urban layouts, and data centers forming the digital core of the city's new systems. What makes the Addis Ababa City Corridor project stand out isn't just its scale, but its symbolism. Ethiopia is positioning itself as a regional leader in technology and infrastructure, and the capital city is its proving ground. The project represents a shift from reactive urban growth to proactive, technology-driven design, an attempt to future-proof a city that's expected to keep growing for decades to come. And when it's complete, Addis Ababa could stand as one of the first truly smart cities on the African continent, built not just to handle its population, but to evolve intelligently alongside it. In a country that's already known for doing things on a grand scale, Lusay City might be the most ambitious vision of all. It's not just another district or a new development on the edge of Doha. This is an entirely new city, built from the sand up, with skyscrapers, marinas, stadiums, and entire neighborhoods that didn't exist just a few years ago. And what's even more striking is that it was all designed to be ready in time for one of the biggest global events Qatar has ever hosted, the 2022 FIFA World Cup. Now, when most countries host the World Cup, they upgrade a few stadiums, maybe improve some roads, and polish the existing cities. But Qatar did something different. They decided to build a city, and not just any city, a futuristic, master-planned urban center that could one day rival major global capitals. That's Lusail. At the heart of it all is Lusail Stadium, a golden, bowl-shaped structure that became the centerpiece of the tournament. It held the opening and closing ceremonies, and it's where the world watched the final match play out in front of a roaring crowd. But Lusail wasn't built just for football. The stadium was only one piece of a sprawling urban puzzle that includes business districts, residential towers, tech hubs, shopping centres, and an entire waterfront lined with parks, walkways, and yachts. It's the kind of place designed not only to impress visitors, but to lay the groundwork for a post-oil economy. Something sustainable, modern, and globally connected. What makes Lusail stand out is how fast it all came together. Less than 2 decades ago, this was just empty desert. No roads, no buildings, just a bold vision and a whole lot of heat. And in that short time, workers and engineers transformed the landscape with underground tunnels, smart grid infrastructure, and cutting-edge cooling systems that keep the city livable even in Qatar's brutal summer. There's a light rail system that zips through the streets, fully integrated into the larger metro network, and nearly everything is designed with energy efficiency in mind. But as impressive as it is, Lusail also raises questions. Will people move there? Will the city thrive after the World Cup spotlight fades? Because building a city is one thing, filling it with life is something else entirely. Right now, Lusail still feels new, still in the process of becoming what it was meant to be. Office towers are waiting for tenants, apartments are waiting for families, and time will tell if it turns into the vibrant, buzzing metropolis that planners envisioned, or if it remains a symbol of ambition more than reality. Still, as a feat of engineering and construction, Lusail City is remarkable. It shows what's possible when you have the resources, the will, and a clear goal on the horizon. Few infrastructure projects in the northeastern United States have so comprehensively redefined regional mobility as the construction of the Governor Mario M. Cuomo Bridge. Spanning the Hudson River between Tarrytown and Nyack, this modern twin-span structure replaced the aging Tappan Zee Bridge, which had served for over 6 decades but was increasingly unable to meet the demands of 21st century traffic, safety, and structural performance requirements. The replacement effort was not only monumental in scale, but also served as a showcase of accelerated design build execution, seismic resilience, and long-span cable-stayed bridge engineering. Construction began with an extensive program of pile driving and cofferdam installation in the river's soft glacial sediments. More than 1,000 piles were driven to create the foundations for the main span towers and approach piers, with many of them extending over 200 feet below the river surface to reach competent strata. These piles were either steel pipe piles or concrete-filled steel cylinders driven using high-capacity hydraulic hammers aboard floating barges. Each pile had to be carefully aligned to meet strict tolerances, and dynamic load testing was performed regularly to verify bearing capacity. Central to the structure are the cable-stayed main spans, each carrying 4 lanes of traffic with additional space for emergency shoulders and a shared use path. The twin main span towers, constructed with reinforced concrete, rise from pile-supported cofferdams and were built incrementally using jump form systems. These towers house the anchorages for the stay cables, which are arranged in a semi-fan configuration and composed of galvanized steel strands enclosed in protective sheathing. Each cable was tensioned individually using strand jacks, and their load paths were continuously monitored throughout installation to maintain even deck camber and prevent distortion. The bridge's deck was constructed using precast concrete panels and structural steel girders. These panels were fabricated off-site and barged to the work zone, where they were lifted into place by gantry cranes and secured with high-strength post-tensioning systems. By utilizing modular construction, the project team reduced field labor intensity and maintained strict quality control over concrete finishes and rebar placement. Simultaneously, orthotropic deck sections were integrated into specific areas where weight savings were essential, particularly near the tower anchorages. Wind loads and thermal expansion across the bridge's more than 3-mile length were key design considerations. Expansion joints with built-in damping systems were installed at each abutment and tower transition. The bridge is also equipped with smart monitoring systems embedded within its structure, capable of measuring strain, tilt, temperature, and traffic load in real time. On the western span, a dedicated bicycle and pedestrian path was constructed, complete with belvederes for scenic viewing and interpretive signage. This element, though minor in structural weight, required careful coordination with the main deck construction to maintain alignment, loading distribution, and railing continuity. The lighting system was also integrated directly into the bridge structure, minimizing the need for maintenance access while providing full-spectrum LED visibility and programmable displays for special events. In the quiet countryside of southern France, surrounded by pine forests and rolling hills, there's a construction site unlike any other on Earth. It's not another dam or bridge or skyscraper. It's a machine built to recreate the power of the sun. This is ITER, the International Thermonuclear Experimental Reactor, and it represents one of the most ambitious scientific collaborations in human history. The goal here is nothing short of mastering nuclear fusion, the same reaction that fuels stars, and turning it into a practical source of energy for our planet. The concept sounds simple in theory, but has pushed the limits of engineering for decades. Fusion happens when two light atomic nuclei, usually forms of hydrogen called deuterium and tritium, collide at extremely high temperatures and fuse into helium, releasing enormous amounts of energy. The problem is that replicating those conditions on Earth means creating and controlling plasma that's hotter than the core of the sun, about 150 million degrees Celsius, and keeping it stable long enough to extract useful power from it. That's where ITER comes in. At the heart of the project is the tokamak, a donut-shaped reactor designed to contain the plasma using magnetic fields so powerful they could lift aircraft carriers. The machine itself is a masterpiece of precision. Its vacuum vessel weighs over 5,000 tons. Its superconducting magnets are cooled to near absolute zero, and every component must align with millimeter accuracy, despite being the size of a small building. The idea is that when the system is fully operational, the reactor will produce 10 times more energy than it consumes, something no fusion experiment has ever achieved before. What makes ITER truly remarkable is how global it is. It's being built through a partnership of 35 nations, including the European Union, China, the United States, Russia, Japan, India, and South Korea. Each partner contributes different components, from cryogenic systems to magnet coils to diagnostic sensors, and all of them have to fit together perfectly when assembled in France. Coordinating that kind of international supply chain is an engineering feat in itself, with massive pieces of hardware shipped across oceans and transported by custom-built convoys that crawl through rural roads to reach the site. The scale of the infrastructure around the tokamak is equally astonishing. There's a massive cryoplant to cool the magnets, a system of vacuum pumps, cooling water loops, radio frequency heating systems, and an entire electrical network dedicated to feeding the experiment's colossal appetite for power. When ITER begins its first plasma runs, it will consume more electricity than a medium-sized city, though the aim is to prove that fusion can eventually produce far more energy than it uses. Yet the challenge isn't just technical, it's also philosophical. Fusion has been called the energy of the future for over half a century, and ITER's success or failure could finally determine whether that future is real. If it works, it could open the door to commercial reactors that generate clean, virtually limitless energy from seawater, with no carbon emissions and almost no radioactive waste. But for now, ITER remains an experiment, a monument to human cooperation and scientific persistence, standing quietly in Provence as thousands of engineers and scientists work to capture the power of the stars here on Earth. Sometimes a project comes along that just doesn't make sense, at least not until you see it, drive across it, and realize what it actually represents. The Hong Kong-Zhuhai-Macau Bridge is exactly that kind of project. It's not just a bridge, it's not just a tunnel. It's a 55-kilometer long leap of engineering that crosses one of the busiest shipping lanes in the world, links three massive cities that used to feel far apart, and proves that China is willing to push infrastructure to extremes in ways few countries ever dare. To understand why it matters, you've got to look at the geography first. The Pearl River Delta is one of the most densely populated and economically powerful regions on the planet, with Hong Kong on one side, Macau on another, and Zhuhai anchoring the mainland. But even though these places look close on a map, getting between them used to take hours. Ferries, detours, congested roads. It was all slow, fragmented, and inefficient. So China decided to stitch the region together with a single mega link, one that could handle freight, commuters, and cross-border travel in one seamless shot. But building it wasn't simple. For starters, the bridge had to survive typhoons, earthquakes, and heavy marine traffic, all while standing in soft, muddy seabed that doesn't exactly love supporting massive pylons. Then there's the tunnel, because at one stretch, the bridge actually disappears beneath the water for over 6 kilometers to make way for ships. That required building 2 artificial islands out in the open sea, just so the road could dip down, dive under the shipping channel, and then rise back up again without interfering with maritime traffic. And that's where the engineering really hits you. The immersed tube tunnel, made up of huge prefabricated sections, was floated out, sunk into a trench, and sealed together underwater. Each section had to fit perfectly, with zero room for leaks or shifts. Above that, the bridge sections were hoisted into place using massive cranes, forming a ribbon of concrete and steel that curves and bends like a sculpture across the sea. When it finally opened in 2018, after nearly a decade of construction, the bridge cut travel time between these cities from several hours down to about 30 minutes. But beyond the time savings, it's a symbol. A signal that the Greater Bay Area is no longer just a loose collection of cities. It's becoming a single, interconnected mega region, one where borders blur and infrastructure drives integration. Of course, it hasn't been without controversy. The cost was enormous, the environmental impact was debated, and questions about who benefits the most continue to come up. But if you're talking about sheer ambition, about looking at a map and deciding to redraw it with concrete and cable, then the Hong Kong-Zhuhai-Macau Bridge stands in a league of its own. At the heart of a massive cross-border logistics corridor between Detroit, Michigan, and Windsor, Ontario, the Gordie Howe International Bridge emerges as one of the most technically ambitious and strategically vital infrastructure projects in North America. Designed as a cable-stayed bridge with an unprecedented main span length for this type of crossing in North America, the structure addresses not only current transportation needs, but also anticipates decades of future commercial and passenger vehicle growth. What sets this project apart is the integration of border processing facilities on both ends, a multi-use path for non-motorized users, and a focus on minimizing environmental impact during construction. Construction of the bridge began with an intensive ground improvement phase. On both the Canadian and American sides, the project required deep foundation stabilization due to soft soils and industrial legacy conditions. Thousands of concrete-filled steel piles were driven deep into the ground, many over 150 feet long, to support the massive load of the main pylons and approach structures. Vibrocompaction and dynamic replacement techniques were also applied in select areas to densify weak soils and ensure long-term settlement control. The signature feature of the bridge is its cable-stayed main span, which stretches more than 2,500 feet across the Detroit River. The two massive towers, each rising nearly 150 meters above the water, were constructed using climbing formwork systems with high-strength reinforced concrete placed in lifts and allowed to cure under strictly controlled environmental conditions. Each lift required careful coordination of embedded rebar cages, conduit for internal inspection systems, and multiple layers of quality control for alignment and geometric accuracy. The stay cables are arranged in a semi-fan pattern and connect to a composite steel concrete deck that is fabricated in modular segments. These segments are lifted into position by strand-jacking gantries placed atop the towers, and then post-tensioned into place as the structure progresses outward from both pylons in a balanced cantilever method. Because of the immense forces involved, cable anchorage zones in the deck were heavily reinforced and constructed using high-performance concrete to prevent cracking and fatigue over the bridge's lifespan. In parallel with the main span construction, the approach structures required extensive use of precast girders and segmental concrete box girders, supported on piers founded on deep drilled shafts and pile caps. Each approach segment had to be aligned precisely with the main span geometry to allow seamless connection once the cantilevers met at mid-span. Expansion joints, seismic isolation bearings, and cable dampers were installed to accommodate temperature changes, traffic vibrations, and potential wind-induced oscillations. Perhaps one of the most unique aspects of the Gordie Howe International Bridge is the inclusion of full customs and inspection plazas on both sides of the river, which had to be constructed concurrently with the bridge. These facilities involve complex building systems, large-scale pavement infrastructure, and real-time data integration with transportation networks. Stormwater management, energy efficiency, and border security technologies were embedded into their design from the outset. They're tucked away in the mountains of Guizhou province in southwestern China. There's a gorge so deep and narrow that sunlight barely reaches the river at the bottom for most of the day. And spanning this massive cut in the earth, high above the mist and cliffs, engineers are building something that almost defies belief: the Huajiang Grand Canyon Bridge. When complete, it will stand among the highest bridges ever built on the planet. A structure so tall that if you dropped a skyscraper from the deck, it would fall for seconds before touching the valley floor. The numbers behind it are staggering. The bridge deck will rise over 600 meters above the river, which means it's taller than most observation towers and higher than the top floor of the Shanghai Tower. To put that in perspective, imagine stacking 2 Eiffel Towers end to end. That's roughly the drop from the roadway to the canyon below. This kind of height doesn't just make for dramatic photos, it turns every stage of construction into a feat of courage and precision. Workers spend their days suspended hundreds of meters in the air, guiding steel cables, assembling segments, and balancing heavy machinery on platforms that hang in the clouds. The Huajiang Grand Canyon Bridge is part of a new expressway that will connect cities across Guizhou, one of China's most mountainous provinces. Historically, this region was isolated by its terrain, deep valleys, twisting ridges, and karst formations that make road building incredibly difficult. The bridge is designed to close one of the biggest gaps, cutting travel times from hours to minutes, and linking communities that once felt worlds apart. In a province known for its poverty and difficult logistics, projects like this aren't just about transport, they're about access, trade, and opportunity. Structurally, it's a suspension bridge, chosen because it's one of the few designs that can handle both the span and the height of the canyon. The main span stretches more than 1 kilometer across, supported by enormous cables that anchor into the mountains on each side. The anchorages alone are buried deep in concrete and rock, absorbing the colossal tension forces that hold the deck steady. Every component must withstand fierce winds, extreme temperature shifts, and the constant pull of gravity across an open void. Even the construction of the towers is an achievement, with cranes and scaffolding perched on cliffs that would make most people's legs shake just looking down. What makes the Huajiang project even more impressive is how it reflects China's relentless drive to conquer geography with infrastructure. Guizhou has become a global showcase for bridge engineering, home to more of the world's highest bridges than any other region. Each one seems to push the limits a bit further. Higher decks, longer spans, faster timelines. The Huajiang Bridge is simply the next leap in that sequence, proving that there's almost no terrain too challenging to cross. When it finally opens to traffic, drivers will glide across a stretch of road that looks like it's floating between mountains, with clouds drifting below and the canyon yawning far beneath. It's one of those places where engineering and nature meet in a way that's both awe-inspiring and humbling, a reminder of what human ingenuity can achieve when the landscape dares us to go higher. Most airports are built on land that's already there. Kansai International wasn't. Instead, engineers created an entirely new island out in Osaka Bay, built an airport on top of it, and then had to figure out how to keep the whole thing from sinking into the sea. That's the challenge Japan took on when it decided to build Kansai International Airport, a project so bold and complex that it still stands as one of the most ambitious examples of modern infrastructure in the world. Back in the 1980s, Japan's major cities were bursting at the seams. Tokyo and Osaka needed more capacity for international air traffic, but there just wasn't enough available land near the city centers. Noise pollution was also a growing problem, especially with flights operating late at night. So planners came up with a radical solution. Instead of expanding on land, they would go out to sea and build an airport where planes could take off and land without disturbing densely populated areas. The result was Kansai International Airport, built on an entirely artificial island about 5 kilometers off the coast of Honshu. But the idea of building an airport in the middle of the ocean came with immediate engineering challenges. The seabed under Osaka Bay is soft, silty, and unstable, exactly the kind of ground you wouldn't choose for a massive, heavy structure like an airport. To make it work, engineers drove thousands of steel and concrete piles deep into the seabed to support the foundation, then placed layers of sand, gravel, and fill to shape the island itself. Even with that foundation in place, the island started settling almost immediately. Engineers had predicted that it would sink gradually over time, but not quite as fast as it did. Within the first few years, parts of the island had already dropped by several meters, forcing teams to constantly adjust and reinforce structures, utilities, and runway surfaces to keep them level and safe. And even now, decades later, the airport is still sinking, although at a much slower rate than before. Maintaining it has become an ongoing process that's just as important as building it in the first place. Despite the difficulties, Kansai International opened in 1994 with one of the most striking terminal designs in the world. The main terminal, designed by Italian architect Renzo Piano, features a long curving roof that mimics the flow of wind and water, a subtle nod to the airport's connection with the sea. It's functional too, allowing for efficient passenger flow and natural ventilation. The terminal stretches nearly 2 kilometers, and it was, at the time, the longest building on the planet. Getting to and from the airport is part of the experience. A dedicated rail link and an expressway connect Kansai to the mainland, running across a long bridge that becomes your first glimpse of the airport as you approach. And once you arrive, the open layout, sleek design, and ocean views remind you that you're standing on one of the most complex man-made structures on Earth. Kansai International wasn't just about solving an airport problem. It was a test of how far engineering could go when land, space, and geography are all working against you. And even though the project has been expensive to maintain, with ongoing challenges due to settlement and typhoon exposure, it still stands as proof that sometimes the only way forward is to build where no one else has dared. As the rising arc of twin basket handle arch bridges took shape over the Mississippi River, the transformation of the I-74 corridor between Bettendorf, Iowa, and Moline, Illinois, entered one of its most critical and technically ambitious phases. The construction of the new I-74 Mississippi River Bridge was not merely a replacement of aging infrastructure, it was a complete reimagining of regional connectivity, driven by modern standards for traffic volume, safety, and structural resilience. The original bridge system, composed of two separate spans constructed decades apart, had long been overcapacity and structurally obsolete, necessitating a solution that would carry 4 lanes of traffic in each direction, with substantial shoulders and multimodal accommodations. Foundation work for the main river crossing demanded meticulous geotechnical investigations due to the presence of complex riverbed conditions. Deep caissons and drilled shafts were deployed to reach competent rock, with many of the drilled shafts extending over 100 feet into the bedrock below the Mississippi's muddy floor. This phase involved the use of massive steel casing, oscillators, and reverse circulation drilling techniques to ensure shaft integrity in an environment challenged by underwater currents and variable sediment layers. Cofferdams were constructed to create dry working conditions for pier construction, each one engineered to resist the high hydrostatic pressures of the river during seasonal flooding. The signature basket handle arch design was selected for both aesthetic and structural performance. These arches rise more than 100 feet above the deck and were fabricated in large segments off-site, then transported by barge to the erection location. The erection sequence was tightly choreographed. Arch ribs were lifted and pinned using floating cranes during periods of calm river flow, with crews performing high elevation bolting and welding operations within tight tolerances. Each arch rib section was temporarily braced and connected via knuckle joints and box diaphragms until the entire arch structure was self-supporting. The steel itself was weathering grade, chosen to reduce long-term maintenance needs and withstand the extreme freeze-thaw cycles common to the upper Midwest. Suspended below each arch is a post-tensioned concrete deck carried by steel hangers arrayed in a vertical configuration. The bridge deck was cast in place, using a traveling formwork system that advanced span by span. Epoxy-coated rebar, high-performance concrete mixers, and continuous monitoring of curing conditions ensured long-term durability. Expansion joints were minimized through the use of integral abutments and deck continuity, reducing maintenance complexity. Parallel to the main river spans, approach structures on either side required extensive reconstruction and realignment of existing highway infrastructure. Mechanically stabilized earth walls and drilled shaft-supported piers form the backbone of the approaches. The coordination of traffic staging during construction was a major challenge, as portions of the existing bridge needed to remain in service throughout the process. Temporary crossovers, stage demolitions, and nighttime steel girder installations were part of a detailed traffic management strategy. If you've ever traveled through Britain by train, you know the experience can be both scenic and slow, with Victorian-era infrastructure still carrying millions of passengers every day. That's exactly what the HS2 project set out to change, a high-speed rail line designed to reshape how the country moves, connecting London with the Midlands and the North at speeds the UK has never seen before. It was imagined as the backbone of a new, modern transport network, one that could rival continental Europe's fast and efficient trains while easing the pressure on the country's crowded existing lines. High Speed 2, or HS2, is being built in stages. The first phase stretches from London to Birmingham, cutting travel times almost in half. The second was originally meant to continue north toward Manchester and Leeds, linking major cities with sleek new trains running at over 320 kilometers per hour. The ambition wasn't just about shaving minutes off journeys, it was about balancing Britain's economic geography, pulling growth and investment away from the capital and spreading it toward regions that had long been left behind. In theory, faster travel meant stronger regional economies, easier business connections, and new job opportunities across the country. But building HS2 has been anything but straightforward. It's one of the largest infrastructure projects in Europe, involving hundreds of kilometres of tunnels, viaducts, and embankments carved through some of England's most densely populated areas. The sheer complexity of the route required boring machines to tunnel under London suburbs, elevating tracks across countryside landscapes, and even designing specially built wildlife bridges to protect local ecosystems. Every section of the project is a microcosm of engineering challenges: soft clay, urban congestion, ancient infrastructure, and a constant balancing act between speed, safety, and sustainability. The construction workforce alone numbers in the tens of thousands, operating across dozens of sites at once. Giant tunnel boring machines, each named and tracked like ships, have been chewing their way through chalk and clay beneath the Chiltern Hills, creating vast underground passageways for the new line. Elsewhere, massive viaducts rise over river valleys, and new depots and stations take shape in cities that have been waiting decades for this kind of modernisation. Euston and Old Oak Common in London are being transformed into vast transport hubs, designed not just for HS2, but to connect seamlessly with existing networks, integrating the old with the new. However, despite its technical brilliance, HS2 has faced intense criticism and political turmoil. Costs have soared far beyond initial estimates, delays have stacked up, and parts of the northern extensions have been scaled back or cancelled entirely, leading many to question whether the project can still deliver on its original promises. Environmental groups have voiced concerns about the loss of woodland and natural habitats, while others argue that the benefits to the broader economy still justify the disruption. Even so, what remains of HS2 still represents a massive leap forward for Britain's rail system. When the first trains begin running between London and Birmingham, they'll mark the country's entry into true high-speed travel, a mode that much of the world has already embraced. And while the vision may have shrunk from its earliest days, the project still stands as a symbol of long-term ambition, the kind of investment that tries to build not just for today's commuters, but for generations yet to come. It's not every day that you take one of the most iconic engineering achievements in human history and decide to tear it open, rebuild parts of it from scratch, and make it even bigger than before. But that's exactly what Panama did with its historic canal, a project so ambitious it was known simply as the Expansion, and it pushed the limits of what was even possible in one of the most important trade corridors on Earth. For more than a century, the original Panama Canal had served as the narrow, vital artery connecting the Pacific and Atlantic Oceans. It was revolutionary in its time, slicing through the Isthmus of Panama and transforming global shipping. But as cargo ships got bigger, taller, and longer, the canal that once changed the world suddenly found itself stuck in the past. The largest container ships, the so-called post-Panamax giants, simply couldn't fit through. That meant Panama was missing out on billions in potential revenue, and the world's logistics network was increasingly having to go around. So in 2007, Panama broke ground on the biggest upgrade the canal had seen since it first opened in 1914. The centerpiece was a brand new set of locks, 3 chambers at each end of the canal that could handle ships more than twice the size of what the old locks were built for. But this wasn't just about size. The new locks used massive rolling gates instead of the old swinging ones, and they relied on water-saving basins that could recycle much of the fresh water used in each transit. In a region where water is precious and unpredictable, that was a game changer. Digging those new channels wasn't easy. Crews had to blast and excavate millions of cubic meters of rock, cut entirely new approaches, and do it all while keeping the original canal running full tilt. And because the canal operates on gravity and freshwater lakes, not pumps, every meter of elevation, every gate, and every water drop had to be managed with insane precision. The scale was mind-bending. Hundreds of kilometers of construction zones, dozens of engineering contractors from all over the world, and thousands of workers battling heat, rain, and mud year-round to make it happen. The expanded canal finally opened in 2016, after nearly a decade of work and a cost pushing over $5 billion. And the results were instant. Suddenly, ships carrying up to 14,000 containers could cross between oceans in under 10 hours. That single upgrade reshaped shipping routes, slashed costs for major carriers, and cemented Panama's role as a global logistics powerhouse. It also gave the country a new sense of ownership, because, unlike the original canal, which was built and long controlled by foreign powers, this expansion was run entirely by Panama itself, from the planning to the operations. It's one thing to build something great. It's another thing entirely to make it even better a century later, especially when the stakes are global and the margin for error is razor thin. Beneath the southern skyline of Portland, Oregon, the Selwood Bridge Replacement Project unfolded as a carefully orchestrated effort to modernize a century-old crossing while respecting the constraints of an urban setting and a sensitive river environment. Originally opened in 1925, the existing structure had long been structurally deficient and functionally obsolete. It carried tens of thousands of vehicles per day on a narrow, deteriorating deck with no shoulders and minimal pedestrian accommodations. The new bridge would not only replace the failing structure, but also vastly improve safety, seismic resilience, and multimodal capacity. The design of the replacement bridge called for a deck arch structure, which would span the Willamette River with minimal disruption to the waterway and surrounding neighborhoods. Prior to any new construction, engineers faced the unique challenge of what to do with the existing bridge. Instead of fully demolishing it up front, a temporary solution was implemented. The original steel truss was shifted laterally, intact, onto temporary piers constructed just downstream. This extraordinary lateral slide operation allowed the old bridge to remain in service while the new bridge was built in its original alignment. The lateral move required precise hydraulic jacking systems and heavy-duty rollers. Crews disconnected the truss from its existing piers and then slowly slid the entire structure onto a set of temporary supports built on drilled shafts. This move, executed in just a few hours after weeks of preparation, cleared the path for demolition of the original concrete piers, many of which had suffered extensive corrosion and were no longer structurally viable. With the original alignment clear, construction of the new bridge began with installation of deep foundation elements, including drilled shafts socketed into bedrock beneath the riverbed. These shafts would support the new reinforced concrete piers, which in turn carried the load of the deck arch. The arch segments were constructed using a balanced cantilever method, with concrete segments cast in place and post-tension to maintain structural integrity as they extended symmetrically from each side of the river. The bridge deck itself was cast in segments atop the arch ribs using a system of falsework and custom-formed travelers. The deck accommodated 2 standard travel lanes in each direction, generous bike lanes, and wide sidewalks on both sides, features entirely absent from the original structure. In addition, the deck design included integrated stormwater treatment systems to capture and filter runoff before it entered the Willamette River. As the new bridge took shape, utilities were relocated, traffic patterns shifted, and seismic isolators were installed beneath critical components to provide flexibility in the event of an earthquake. Steel reinforcement was designed with corrosion resistance in mind, and all concrete elements were specified with admixtures tailored to the region's wet climate. Once the new structure was complete and fully operational, the old temporary bridge was dismantled and removed from its temporary supports. Final phases included landscaping, approach road improvements, and installation of aesthetic lighting and railing features to blend the bridge with its urban and natural context. In the vast emptiness of northwestern Saudi Arabia, where desert and mountains stretch endlessly under the sun, a line of glass and steel is being drawn across the landscape. A city unlike any that has ever been built before. It's called the Line, and it forms the central vision of NEOM, a futuristic megaproject meant to redefine what urban living can be in the 21st century. The idea sounds almost impossible at first, a city that isn't sprawling outward, but extending straight for hundreds of kilometers, only 200 meters wide, yet home to millions of people. But that's exactly the scale of ambition Saudi Arabia is pursuing, nothing less than the reinvention of civilization itself. The concept behind the Line begins with simplicity. Instead of spreading a city outward in all directions, it compresses everything into a single linear corridor that runs through desert valleys and over coastal plains. The two mirrored walls of the city rise more than 400 meters, enclosing a narrow interior where people will live, work, and travel vertically rather than horizontally. The structure is designed to function as a continuous vertical metropolis where everything, from housing and offices to schools, parks, and public transit, is stacked efficiently inside a climate-controlled environment. At its core, the Line is meant to operate without cars, roads, or traditional streets. Instead, it relies on a high-speed underground transport system that can move people from end to end in minutes. The idea is that every daily need, groceries, healthcare, education, recreation, should be within a 5-minute walk. By eliminating cars and long commutes, the designers aim to create a city where time is reclaimed for people, where nature and urban life coexist without one overwhelming the other. Sustainability sits at the center of the entire plan. The Line is being built to run entirely on renewable energy, primarily from solar and wind power, and its compact footprint minimizes land use and environmental impact. The vertical design allows the surrounding desert and mountains to remain untouched, preserving natural ecosystems while housing millions of people in a fraction of the space that a normal city would require. The structure's mirrored facade isn't just aesthetic. It reflects sunlight to reduce heat absorption and helps control the city's internal temperature. Engineering something of this magnitude pushes the boundaries of what's physically possible. The foundation requires precision construction over uneven terrain, and the structural demands of building two continuous walls, hundreds of meters high, across such distances are immense. The integration of transportation systems, data networks, energy grids, and vertical living spaces has to function seamlessly for the vision to work. Every part of the city will be monitored and managed through AI-driven systems, adjusting lighting, temperature, and logistics dynamically to optimize efficiency and comfort. The Line also represents a broader idea about the future of Saudi Arabia. It's not just a mega project, it's a statement of national transformation. It reflects the country's drive to diversify beyond oil, to attract technology, investment, and global talent, and to present itself as a center of innovation. For the government, the Line is both an economic experiment and a symbol of ambition, projecting the image of a nation willing to take risk to shape the next century. Whether it succeeds or not, the Line is already changing the conversation about what cities can be. It's forcing engineers, architects, and planners around the world to imagine new forms of living, new ways of organizing society, and new relationships between humans and the environment. In the middle of the desert, a city that runs in a straight line may seem improbable, but that's precisely the point. It's a bet on imagination and on the belief that the future doesn't have to look anything like the past. There's a stretch of highway in southern France where drivers suddenly find themselves suspended in the sky, so high in fact that they're actually above the clouds. That's not poetic exaggeration, that's the Millau Viaduct, one of the tallest bridges in the world, and a mega project that pushed both structural design and aesthetic ambition to new heights. literally. The story of the Millau Viaduct starts not with engineering, but with frustration. For years, travelers moving through the Tarn Valley, especially in the summer, were stuck in endless traffic jams around the town of Millau. The region's rugged terrain made road construction difficult, and the narrow valley routes couldn't handle the growing number of vehicles. A bypass was needed, and the only logical way to make it work was to go over the valley instead of around it. That's when the idea of a viaduct, a long bridge-like structure crossing the entire gorge, began to take shape. But this wasn't going to be any ordinary bridge. The span needed to be long enough to cross the entire Tarn River Valley in a single, clean sweep, and high enough to avoid disrupting the delicate environment below. That meant building a multi-span cable-stayed bridge more than 2.5 kilometers long, with a road deck floating nearly 270 meters above the river at its highest point. That's taller than the Eiffel Tower. And it's not just tall, the structure is elegant, sleek, and razor-thin, blending into the landscape with minimal visual weight despite its colossal size. The design was a collaboration between French engineer Michel Villelogeux and British architect Norman Foster. Villelogeux handled the structural genius, while Foster added the graceful visual language. Together, they created a design that looks light but performs under massive loads. The bridge has 7 pylons, each supporting a section of the deck with cables arranged in a fan pattern. The tallest pylon reaches 343 meters from the base to the tip, making it the tallest bridge support in the world. Building it required extraordinary precision. The deck was constructed in segments and launched outward from each pylon using a method called incremental launching. That meant carefully pushing out steel segments over thin temporary supports, balancing the structure as it stretched across empty space. Crews worked at incredible heights, often exposed to winds and weather, with every component measured to the millimeter. The alignment had to be perfect. Any misstep would throw the entire bridge off balance. The Millau Viaduct opened to traffic in 2004, and the transformation was immediate. The days of traffic crawling through Millau disappeared, and the journey across the valley became something drivers actually looked forward to. You don't just cross this bridge, you experience it. There's a moment, especially early in the morning, when the valley below is still filled with mist, where the road seems to float above the clouds. And for a few minutes, you're not just driving, you're soaring. But beyond the visual drama, the Millau Viaduct is a textbook example of how a mega project can solve a real-world problem while also becoming a piece of national pride. It's functional, efficient, and yet built with a sense of beauty that makes it far more than just infrastructure. Unlike conventional bridge construction that relies on in-place assembly over active roadways, the 2nd Avenue Bridge replacement over I-94 in Detroit took a bold and modern approach, building the entire structure off-site and moving it into position in a single, coordinated operation. This method, known as self-propelled modular transport, allowed engineers to reduce highway closures dramatically while executing a highly complex structural replacement with precision and control. The original 2nd Avenue Bridge was a narrow, outdated crossing that no longer met the safety or capacity standards required for urban connectivity in the Midtown Detroit corridor. With the ongoing modernization of the I-94 freeway, it became essential to not only replace the bridge, but to do so in a way that minimized impacts to one of the busiest traffic arteries in the state. Traditional staged construction would have required extended lane closures, ongoing detours, and multiple phases spread out over months or even years. Instead, the project team designed a new, wider bridge structure that would be constructed entirely adjacent to the interstate in a staging area. This new structure, composed of steel plate girders and a concrete deck, was built on temporary supports known as false work towers. The substructure, comprising abutments and approach walls, was prepared well in advance at the final bridge site, using cast-in-place concrete supported on deep foundations, including driven H-piles embedded into firm strata beneath the interstate. Once the off-site construction was complete and all systems verified, the move operation was scheduled for a carefully planned weekend closure of I-94. The actual bridge move was performed using SPMTs, multi-axle, computer-controlled transport platforms capable of lifting and carrying massive loads with millimeter-level accuracy. The entire superstructure was lifted off its temporary falsework supports using hydraulic jacks integrated into the SPMTs. The system then slowly transported the bridge across the staging area, maneuvering over prepared access paths and aligning itself precisely with the final bridge bearings. During this process, crews on site continuously monitored bearing alignment, elevation, and lateral position, ensuring the bridge matched its abutment seat locations exactly. Once the bridge was in final position, it was slowly lowered onto elastomeric bearings, and mechanical connections were secured to tie the structure into the existing roadway network. The final stages of the operation included backfilling approach zones, paving transitions, and installing barriers and utilities, all tasks that had been prepared in advance to accelerate reopening. One major advantage of this move-in-place approach was that it compressed months of disruptive work into a matter of days. Rather than subjecting the corridor to prolonged construction noise, lane reductions, and detours, the SPMT method enabled a near instantaneous installation with minimal long-term disruption. Down on the shores of the Red Sea, where the old port city of Jeddah stretches out between desert and water, two enormous projects are quietly redrawing the map: Jeddah Central and Jeddah Economic City. Together, they represent a vision of transformation unlike anything the city has seen before, turning this historic gateway into a modern global hub for business, culture, and tourism. What makes these developments remarkable isn't just their scale, but the way they weave old and new, ambition and heritage, into something that feels distinctly Saudi, yet unmistakably international. Jeddah Central sits right in the heart of the city, taking over more than 5 square kilometers of waterfront that once housed the old desalination plant and underused industrial land. It's being reinvented as a new downtown, built around a sweeping marina and a waterfront district lined with cultural landmarks, residential towers, and entertainment spaces. The master plan revolves around 4 main landmarks: a sports stadium, an oceanarium, an opera house, and a museum, all designed to anchor Jeddah's identity as a cultural and leisure destination. Around them will rise luxury hotels, office towers, parks, and promenades, all connected by shaded walkways and open public spaces, meant to bring life back to the seafront. But this isn't just about aesthetics. The project's layout is designed around sustainability and smart urbanism, integrating renewable energy, green transport systems, and water recycling technologies suited to the coastal climate. It's a major shift for Jeddah, which has long struggled with congestion and uneven urban growth. The plan envisions a livable, walkable downtown that balances modernity with comfort, turning the Red Sea coast into a showcase for the new Saudi lifestyle that's emerging under the country's Vision 2030 framework. The idea is to create not just buildings, but experiences, places where art, commerce, and everyday life blend seamlessly. A short distance to the north, Jeddah Economic City takes that ambition and scales it up to a global level. This is the site of the Jeddah Tower, the skyscraper that aims to surpass 1 kilometer in height and become the tallest building in the world. The tower is the centerpiece of a vast mixed-use development covering more than 50 square kilometers, designed to serve as a new economic hub for trade, finance, and innovation. When complete, Jeddah Economic City will have residential neighborhoods, educational institutions, business districts, and green open spaces all linked together by advanced infrastructure and digital systems. The city's design places a strong focus on integration with the wider region. Ports, highways, and logistics corridors will tie it directly into the national network that connects Jeddah to Makkah, Medina, and eventually Neom, farther north. In many ways, Jeddah Economic City represents the country's broader push to diversify its economy beyond oil, creating new industries that can attract global investment and talent. Taken together, Jeddah Central and Jeddah Economic City show two faces of Saudi Arabia's urban transformation. One is cultural and civic, centered on lifestyle and heritage. The other is economic and technological, reaching for the future through engineering and ambition. Both are shaping a new identity for Jeddah, a city that once served as the gateway for pilgrims, now evolving into a gateway for ideas, enterprise, and modern urban life along the edge of the Red Sea. In the highlands of Ethiopia, right near the border with Sudan, a wall of concrete now stretches across the Blue Nile, a dam so massive that it's already reshaping not just the country's energy supply, but the politics of an entire region. This is the Grand Ethiopian Renaissance Dam, often shortened to GERD, and it's one of the most controversial and ambitious infrastructure projects in Africa's modern history. From a purely engineering standpoint, GERD is enormous. The main dam structure stands over 140 meters tall and spans nearly 2 kilometers across the Nile. Behind it, a reservoir capable of holding more than 70 billion cubic meters of water is slowly taking shape, making it one of the largest man-made lakes in Africa. And the hydroelectric potential is just as impressive. When fully operational, GERD is expected to generate over 6,000 megawatts of electricity. That's more than doubling Ethiopia's entire power capacity and turning the country into a potential electricity exporter for the whole East African region. But building this dam was never just about power. For Ethiopia, it's a matter of sovereignty and development. For decades, the country has relied on foreign energy imports and struggled to bring electricity to its rural population. GERD is seen as the key to unlocking long-term economic growth, creating jobs, supporting industry, and expanding access to power across millions of homes. It's a project that has been paid for largely through domestic funding, with the government encouraging citizens to invest in national bonds and support the construction financially and symbolically. That national pride, though, is matched by rising tensions downstream. Both Sudan and Egypt depend heavily on the Nile for irrigation, agriculture, and drinking water, and Egypt in particular has historically viewed the river as a lifeline. For generations, water treaties dating back to colonial times guaranteed Egypt a dominant share of the Nile's flow. Now, with Ethiopia holding back massive volumes of water behind a new dam, those old agreements are being tested. The fear from Cairo is that GERD could reduce the flow of water downstream, especially during the filling period of the reservoir, which could hurt Egyptian agriculture and water security. Ethiopia argues that the dam will actually help stabilize flow, reduce flooding, and benefit all three countries in the long term. But so far, years of negotiations haven't produced a final deal, and the disagreement has created real diplomatic friction, with threats, warnings, and political standoffs becoming more frequent. On the ground though, GERD is nearing completion. The first turbines are already spinning, and power is being delivered to the grid. Construction has taken over a decade, involving thousands of workers and a coordinated effort to bring in materials and equipment through difficult terrain. The logistics alone were staggering, given the remote location and the scale of the build. Whether GERD becomes a unifying symbol of African development or a long-term source of conflict depends on what happens next. Cooperation is still possible, but so is escalation. It's not every day you see a desert city trying to rewrite the global skyline, but that's exactly what's happening in Riyadh right now, as the Rise Tower begins to take shape. planned to reach over 450 meters into the air, this soaring structure is meant to become the tallest building in Saudi Arabia's capital, and one of the tallest in the entire Middle East. But more than just height, Rise Tower is about a statement, one of ambition, reinvention, and a new kind of identity for a city that's transforming faster than most people realize. What's striking about this tower isn't just the glass and steel, it's the setting. Riyadh has always been a low-slung city built to survive the desert, a place of wide roads and sprawling neighborhoods. But Rise Tower is breaking that mold completely. It's anchoring the King Abdullah Financial District, a mega project that's aiming to turn the city into a global hub for finance and innovation. With futuristic architecture, high-tech infrastructure, and walkable urban design, right in the middle of the desert heat. Now, designing something this tall in Riyadh isn't as simple as copying a blueprint from New York or Shanghai. The tower has to deal with harsh sunlight, extreme heat, and powerful desert winds. So everything from its orientation to its skin is being engineered to handle those forces. Think of deep shading fins, high-performance glass, and an internal cooling system that helps balance comfort with sustainability. It's a blend of modern high-rise engineering and climate-specific design, and it has to work flawlessly to support not just offices, but residences, hotels, and observation decks stacked layer after layer up into the clouds. But there's also a symbolic layer to this. Rise Tower isn't just an office building with a fancy spire. It's part of a broader push to redefine what Saudi cities can be. It's coming at a time when the country is pouring trillions into development projects, from Neom to Diriyah. And Riyadh is being positioned as a global destination in its own right. So when you build a tower like this, you're not just constructing floors and elevators. You're constructing a future image, something that says, this is who we are now. And the engineering muscle behind it is just as intense as the vision. You've got mega piles drilled deep into the desert floor to support that much vertical load. You've got cranes operating at dizzying heights in a climate where metal burns to the touch by midday. Logistics, labor, safety, it's all being choreographed at a massive scale to keep everything on track. Because once you start reaching that high, every little mistake becomes a very big problem.